think some people will still take notes because there will be things we say that might you might deem important to remember later. But for the most part, it's all here for you to access. Just getting it, and let us know if there are any issues.
You can go ahead. You can go ahead.
So the speed of sound lab, very standard one. But we have some variations to it that you may not know about. And this is a lab in the conceptual physics lab manual called Mach 1, I believe. And I put a copy of that in my folder. We have a tube of water. Mainly what that is for is to plug one end of this pipe. So it doesn't really matter what kind of pipe you use. I've even used rolled up file folders. It works for a while submerged in water. Some people have a plunger that seals one end like a piston. That works really well. But most people just use the water because it's real easy to change how long the part of the pipe with air in it is. And then we have a tuning fork. And tuning forks usually have the frequency stamped on them. This one happens to be 341.3, very, very accurate. And you excite the tuning fork. And find where it resonates. And then students, it really helps to have multiple people doing this, get accurate results. Students can measure the distance from where the water is to the open end of the pipe. And that is 1/4 of a wavelength because we have a pipe with a closed end and an open end. Technically, the antinode is sticking out a little bit from the pipe. And there are some formulas that will correct for that. I never really found that necessary to do. It comes out pretty well, especially if you have maybe each group with a different frequency and then they average their results. Another variation of this, now my phone is being used to do the camera work here, but I have an app on my phone that generates whatever frequency I want. It's just signal gen. There's all kinds of them. Depends on what kind of phone you have. Just search in your app, or what do they call it on Google, the Google Play or something, or wherever you find your apps on your phone, look for signal generator or frequency generator. And then you can, and the students will do that as well. They're free. Sometimes they have little ads on them and stuff. And then instead of the tuning fork, when you generate a signal with the phone, it's continuous. So it's much easier to find where it is. And then you can let's see, this is your remote. Is there a mute on this?
Blank, I think.
Bottom left corner.
Ah. Well, I don't want to mess up your stuff.
Oh, that's fine. You can erase that. That was just.
So we know for speed is distance over time. And if it's a sound wave, a good distance to use is the wavelength. And the time it takes one wavelength to move past you is the period. But we also know the period is 1/, the frequency. So you get the standard wave speed formula, wavelength times frequency. But this one's a little more interesting. If I rearrange this, I get the wavelength is the speed times the period. That's a lambda, sorry. There. And so if you like doing linearizing with your students, if that's y, and then you put the period, because you can get the period from the 1/, the frequency of your tuning fork or the frequency you're using on your phone, then you get this, points, best fit line, and the slope, swap, The slope is the speed of sound. That's a more of a methodical, experimental way to go about it. And if the students are using the phone app, it's real easy for them to get 4 or 5 data points, however many you want them to have. Or you can have groups share their data and then have a class approach. So I really like this extra approach to it. Another variation I learned at a PTSOS workshop. Let's find where this was again. There. And so that is about 23 centimeters. So you could figure out the speed of sound if you want. 4 times that is the wavelength, and this again was 341 hertz. But what did I forgot what I just said.
23.
23. So what about, that's in air, right? Speed of sound in air. If it's through a different medium, different wave speed. So what I'm going to do is put just some tape over the bottom of the tube. Not to totally block it though, but to use it to prevent these Alka-Seltzer tablets from coming out. Well, that should work. So now, well, it's not, these are off-brand, not true Alka-Seltzer. So these should fill the tube with CO2. Blop, blop, fizz, fizz. Oh, what a relief it is. It's not too old. Let's see on, I can't believe I ate the.
Where's the beef?
Okay. That's Wendy's. It has nothing to do with Alka-Seltzer.
Well, Wendy's comes first, then the Alka-Seltzer.
Okay.
If you get the bacon eater anyway.
So if this is working right, the tube is filling up with CO2. If it's the same, I'm just going home. It's a little different. It's 21. It's not quite full. We can wait a little bit. Okay, let's try one more time here. It's about 19 now. So significantly different. So you can measure the speed of sound, and but it's probably a mix of CO2 and air the way I was doing it. But this is just a giant graduated cylinder that you steal from the chemistry department. If you know the frequency, you can figure out how deep the water needs to be ahead of time. And so if you're having students do this at home, which again they can, because they can get the app in their phone, they can roll up a piece of cardstock and just a heavier paper, and they can do it in a bucket or a deep sink or something. Let's go on here. Any questions on that one?
One thing I just wanted to add is when I do this, I also have them repeat the procedure, but with a pipe that's open on both ends, and I've got the PVC pipes of different diameters so they can kind of telescope it out.
And it will resonate with open ends, right?
It's not as loud as the closed pipe in the water, so you kind of have to have one student kind of holding it next to their ear, but you can't tell.
And that'd be a half wavelength.
And then it would be a half wavelength.
So you have open.
There's a product called shoot, of course I forgot the name, but they're tubes of color that come with different
Boomwhackers.
Oh, yeah.
so those are
The boom-
great for that.
The Boomwhackers, you hit, and then it makes it like a sound, yeah. And if you hit with a closed hand on those, you get a different sound than if you hit just with your finger. Because when you're hitting with the finger, it's sort of like two open ends. And if you hit with your hand, it's too close. We don't have Boomwhackers though. That would definitely be something we could add to PTSOS. So Tom covered, I think, Doppler Shift pretty well last time. I just didn't have my slide, I think, in the file there. So I think I'm just gonna go past, but there's some Doppler Shift simulations. I think, did we show the Simpsons clip?
I think we did.
I think we did.
And the Big Bang clip.
Yeah. So here's another one. So I call these music box guts. So my camera's on, right? Can't see it. Oh, Abigail just brought in some Boomwhackers. How about when I go over this and we'll go back to that. She got all excited when she figured out it was Boomwhackers. I did not know. Is that really my video showing?
Yes,
It's like,
it's from your laptop.
shouldn't it be my camera view though?
No, your camera view would be from when you pull the wide angle camera up on your screen.
Well, that I can do. Might as well just do that since that's working. So it's the mechanism inside a music box. So if you want to find these, if you search music box mechanism, that's a little easier. And this is a kind of a cool one. It's a song everybody knows and loves. Everybody hear that? Oh no, nobody? Name that tune. Anybody online know it?
Here comes the sun.
There you go. Yeah, it's
Point to Sheila.
I think I'm at about 50% on that one. So what is going on with that? You turn the crank. This one's maybe a little louder than other ones. Where's the?
Here's,
Yeah, like here's one.
here's one.
This one just has like, I don't know, itsy bitsy spider or something. This one you can hardly hear at all, but when it's on a surface, then you can hear it. So what is going on? I was puzzled by this. It seemed to me that when it was louder, more energy had to have been coming from it. And why would it generate more energy? I think that was the wrong question. That's the wrong question there. Where does the energy come from? It's really there all along. It's just, what does it do? When I'm holding it, it's heating up my hands. You know, I'm holding it, the vibrations that it's making go into my hands aren't generating sound. Somebody once said it was an impedance mismatch. It's not able to get my fingers to vibrate. They don't vibrate well the way the atoms are put together. But if I put it on a hard surface, same amount of energy, but now a lot of that's going into sound. Old McDonald. And what's really cool is if you put it on your head, you won't be able to hear it. I can hear it really well. you'll be able to try that out if this is one of the raffle items that you get. So everybody will get music box. Got a choice of that in the raffle. If you want to buy your own, I put a link there. But again, if you search crank music box mechanism, you can find them. If we were all in person, everybody's doing it on their head, except him.
My signal, put it on your desk. Okay, now put it on your desk or table.
Okay, so we'll just have to maybe have everybody get theirs out at some time in the future. And so the one I got, Here Comes the Sun one, that was a new discovery. They had other Beatles ones. They were a little bit more, but that's what this one is. But if you search this on Amazon, you'll find the cheaper ones. Okay. So this is something that Tom has. You want to talk about your Yacker tracker, and then I'll show you my weak attempt to make one.
Sure. So, can you turn the camera over this way? So this is a device called a Yacker tracker. This was originally marketed as a classroom management tool. I use it to demonstrate the decibel scale. So the decibel scale is a logarithmic scale, like the Richter scale is. You think, 80 decibels doesn't sound like it's a much larger number than 70 decibels, which doesn't sound like it's a much larger number than 60 decibels. But every time you go up by 10 decibels, you're actually increasing sound intensity by a factor of about 10. So 80 decibels is 10 times as loud as 70 decibels, which means it's 100 or 10 times 10 times as loud as 60 decibels. So to demonstrate this, so the way this works is you can set it anywhere from 50 to 110 decibels. And the way this is marketed is, okay, let's say your class is supposed to be working quietly. You can decide quiet work might mean never exceeding 70 decibels. So you turn it on. And as long as the ambient noise is 70 decibels or less, it doesn't go off. Notice I'm already. But if the kids get too loud, and that goes off, a cranky teacher person can say, "Detentions for everybody." So what I do is I always start low, started on the 50 decibel scale, and I challenge my class not to set it off.
Not easy to do.
So somebody always at this point has to cough or sneeze or something. And then we kind of crank our way up. And then once you get up to about 80, this is where you have to start trying to set it off. So as I'm getting close to 80, then it goes yellow. Hey! The funnest part though, and I always try to remember to warn the teachers on either side of my classroom that I'm going to be doing this. But I've done this enough years that they're used to it if I forget. I set it to 110 decibels, and I tell the class, feel free to come on up, get out of your seats, get as close as you want. And if you can set off the red light at 110 decibels, I will give everybody in the class 50 extra credit points. So everybody comes up here, and they're just flipping, screaming at this thing. And they can't even turn it yellow. And after a couple of minutes and they're red-faced and panting, I say, okay, well, I guess you didn't want the extra credit very bad, so sit down. And then I explain I've never had to award any extra credit points for this particular activity. So this is something that I bought that was pre-made for this. Dan has kind of a nifty kind of DIY version.
So let me go back to that. So I don't see a way to do this as distance learning unless you had one of these. in your house and they could be yelling through their the Zoom or something. But there are apps for phones that measure decibels, so you can certainly come up with a activity for students to find a place in their neighborhood that's the quietest and place that's the loudest, and they can do some interesting things with that. The Yacker tracker is still sold and available. Here's a product video, and then I found this YouTube video where they have it in a hospital by the nurses station. And so the nurses sometimes, when they're not doing their rounds or whatever, they get talking and they get a little loud and it disturbs the patients. So they decided to get one of these it doesn't do the siren thing, but it tells them when they're getting a little too loud so the patients can have a little more quiet. And what I did is at Pasco, we have this thing called the wireless light source. And I was always an admirer of Tom's Yacker tracker, so I decided to make my own. So this is a SparkView file, and SparkView, again, you can download it for a free 180-day trial if you want to try out things. And we have an ability to code. And so this is called Blockly code. And I created that to make a Yacker tracker. And I can set what decibel levels I want to make it turn green, yellow, or red. So I have it on, and I just need to connect to it. So it connects wirelessly. And if I hit start, so it's displaying the decibels. Let's see, it should be on. It was working before, huh? Hey, it's not coming on now. Let's try again. Might have run the bet now. Well, that's embarrassing. I'm trying to show something. Let's try again. Hey, no. Should this be green? That's weird. It was working. One more time. On. Oh, wow. I'm gonna try one more thing here, bear with me. I think it's because I turned it off while I was using it. It did work though. Tom, will you verify that
It
it worked?
did work. I will witness.
Yeah. It might be you need to update your SparkView. I don't think that's it though. So it's working. There we go. So it's displaying. Let's make it so you can see. So it's green. Hey, it's too loud. So it works. The yellow's a little harder to see, right? Yellow, red, yellow, green. But the Yacker tracker is about the same price, so it's a lot bigger. Okay, got it to work at least. So I did put that SparkView file in the handouts if you're interested in that version. And this is just something that I've shown for a long time. It's an online source. Sometimes it goes away and comes back, but it's just kind of, you show optical illusions there are also auditory illusions, and you can find those online just by searching them. But this sort of classic research that they did, they created this set of 39 demonstrations, and you can get to it from that link, unless they took it away again. There you go. And so you can download it. It says campus only. So it's there, but maybe I'll let you guys find out. But there are two in here. One just shows the decibel scale.
At various distances from the microphone.
I am now speaking to you from a distance of 25 centimeters from the microphone. I am now speaking to you from a distance of 50 centimeters from the microphone.
And it goes on like that. So it gives you an idea of the decibel scale. And again, there are 39 of these. This is my favorite, though. This is the auditory illusion.
Circularity in pitch judgment.
Oh, it's not working.
Two examples of scales that illustrate circularity in pitch judgment are presented. The first is
When I go to that, it goes off.
The first is a discrete scale of Roger N. Shepard. The second is a continuous scale of Jean-Claude Risset.
Not hearing it at all. Those. How about this?
A tiny bit, you can hear it.
That's weird. So I think I have it. So computer audio should be working, right? Wasn't it working before? I see.
You hit share screen. Make sure that you have shared computer audio.
Oh, that was it. That was okay. Your screen sharing.
Down the bottom left hand corner.
Is it in a more? Maybe? Oh, there it shares sound. Okay,
Circularity in pitch judgment.
now it's working.
Two examples of scales that illustrate circularity in pitch judgment are presented. The first is a discrete scale of Roger N. Shepard. The second is a continuous scale of Jean-Claude Risset.
It's sort of like an Escher auditory.
It makes me picture Bugs Bunny sneaking up on Elmer's phone.
So those two are embedded in the slides, and if you're interested in the other ones, that link gets you to it. It said campus only, but I'm pretty sure I clicked on it and they all just downloaded. How are they going to know you're not on campus? Let's see. So before we go on to Whirly Tubes, got the Boomwhackers. You want to demo them? I've never done anything with these at all. So it's just the whole tube. These would be good for the speed of sound lab too, right? That's all there is to it. Definitely a different sound. So if I go like this, it hurts. That's what happens. Definitely a higher tone.
Well, it hurts because it's related to frequency.
Whacking against the edge of a table works really well. You don't have to do it.
I like the.
Well, I wanted to do it, so that's an open, the tube open on both ends. If you go like that, it's closed. It's sort of apples and oranges, but yeah, it hurts to do that, so I wouldn't have students do it. Those are Boomwhackers. They look inexpensive. And you could probably, I think, with a sound sensor, even try and measure the frequencies to compare it to what the ideal should be. Want to show them the Whirly Tubes, and then I'll just talk a little bit about it.
Here's another little device.
These don't hurt. So the advertisement's 5 tones. Can you get all 5 tones? 1, 2, 3, 4. Oh, I have to send them back. No, I think you can probably get a 5th one there even faster. So I call them Whirly Tubes, but just Whirlies. And so the key thing is it's corrugated. If you try it with, I don't know if there was a piece of hose. I think I gave it to you, Tom, but you probably have no idea where that is. But if you spin a tube that's similar, but it's not corrugated, no sounds come out. And so the corrugation is responsible for the vibrations that happen because the airflow isn't uniform over it. There's a fundamental frequency that is twice the length of the tube. That one you don't hear. The airflow is too slow. And so even with the corrugation, you don't get enough vibration to hear it. And so the notes that you hear, are 2 times the fundamental and on up. And so you can measure the frequencies. Again, there are phone apps. I showed Audacity last time, and that will measure the frequency of a sound. But also there's an app called FEFOX. But there's a lot of frequency analysis apps that will measure the frequencies. And the reason the air flows through it, now I'd always heard it was the Bernoulli effect, as that end is spinning around, you get a low pressure there because the air is going fast over it, and that carries the air through it. It isn't that. It's the air in the tube, you're trying to get it to spin in a circle. Well, there's no force pulling it toward the center to make it go in a circle, and so it can't. So imagine filling the Whirly tube with a bunch of confetti or something. And you know, if you spin it, it's going to flow through the tube and come out. That's what happens to the air. There's a lot about Whirlies on Paul Dougherty's webpage. He also gave a talk to the AAAS, which is very interesting. It's just his notes for the talk, but I found that very fun reading. There are people that are professional whirly people. Well, Tom is one of them, but Sarah Hopkins is also a pro and does whole symphonies here. Okay, everybody turn the lights down and lay back. This is our mindfulness meditation moment.
They're such beautiful instruments and they're so easy to play.
That's a different technique she's showing there. That got Tom's interest.
Imagine 5,000 people using harmonic whirlies to create a moving dot painting. Everybody can play them.
That is there for your viewing enjoyment. And so she met with Paul Dougherty once, and that's how I got that link. Paul has also done things like, what is the largest whirly? And if he sees a corrugated, or he's no longer with us, but whenever he saw a corrugated pipe of some sort, he would instantly grab it and start spinning it around to see if he could get sounds out of it. I'm seeing Tom's air track tubes, air supply tubes. He would be spinning those around. And Arbor sells them $2.95. If you search, you can probably find some cheaper prices. And a whirly is one of the raffle items. But it's really good to get one in the hands of every student, not just every lab group. But every lab group would be great. And here's what that might look like. Okay, the next note up. And higher. I think they're a little too close together here. It's kind of dangerous. But nobody was hurt, as far as I know. So that is sound. Do you have any other sound stuff?
Oh, just a couple of things. This is just another little quick demo for how changing the length of an air column changes the pitch. Gives you a chance to be your own little sideshow Bob there. Another demo that I do using the same app that Dan mentioned earlier, the signal generator app. So I have a little Bluetooth speaker here. These are actually surprisingly cheap. I think I got this for like $40 on Amazon, and they're a surprisingly good speaker. I use it at home just to listen to music. But if I hook up my phone to it, aren't we turned on? Yes. So I'm going to go on, I'm going to use the Signal Gen app, and it lets me pick any frequency as low as 0 and as high as 20,000 and play it through my speaker. So we use this to test, the range of human hearing is supposedly 20 to 20,000 hertz. Well, you can experimentally verify that. So I like to start really, really high. And so now I am at 20,000 hertz, and I don't hear it. And I'm slowly cranking it down. Now, usually it's around this point, it's about 16,000 hertz right now. I still don't hear it. It's usually around this point, my students are starting to wince like crazy, like, oh God, stop it, which is part of the fun of the activity. Now I'm starting to hear it about 14,000.
I can't.
Anybody else hear it? 13,000.
You can hear
It is
Coming up.
really piercingly loud to me.
He's Josh.
12,000,
Now I can hear it.
Okay, I hear something.
11,000,
Okay. Now I'm hearing it.
10,000. And then you can,
Wow.
when you can. Down to about 300 hertz now. Oops. Commence primary ignition.
So this is what you could use in the speed of sound lab. You could use this app too it comes right out of the phone.
And before we leave, I just wanted to show you, I'm not going to take you through all my slides, but I just want to show you what my slides look like so you can see what resource is available. So, let's see.
I have it set up with like window mode.
So if I bring up,
So no, your slide should be there. Did you want your
I
slides?
was just going to show my website.
Okay, good.
So here's my overall homepage. If you click PTSOS files, I think that's takes you to the page that you were given the link to earlier. And so I have pretty much all of my PowerPoint slide decks that I wrote this year. So, you know, in the before time, I tended to do most of my lectures just up at the whiteboard, you know, explaining stuff in real time and drawing diagrams in real time, and that just wasn't an option this year. So I spent a good chunk of my summer vacation last year taking all of my lectures and putting them into PowerPoint form. And then I posted all of that to this page. So I've got all of my lecture slides for, this is for my IB physics, oops, come back here. My IB physics class. My IB physics class pretty much covers everything that you could possibly cover in a first year physics class. And then to modify, so the IB physics class is kind of an honors level class. And then I kind of modify these slides to make them more appropriate for a regular physics class. But any topic that you might think of is probably on here somewhere. So for example, lesson 4C, sound as a wave. If I bring that up. So just to show you kind of what my style of slideshow is like. So this is my lecture. So I would assign students. So I also recorded an audio component to this, but I post this online and students take notes from it. I love this GIF. This GIF here, and I refuse to utter the soft G. But this GIF here is, I think, really wonderful for showing how sound is a longitudinal wave, and B, how a wave is a way of transferring energy from point A to point B without material. If you keep your eye on just one of the little red dots, notice it just vibrates back and forth. Emphasize that every sci-fi movie where you hear things in space is a lie. And then I get into my lectures, which I'm not going to go through here, but just so you can see what the resource is. So here I go through, Dan mentioned earlier how resonance works in a closed versus an open pipe. I go through why that happens, why 1/4 wavelength for closed, why 1/2 for open. Go through some example problems. Here's my slides on the Doppler effect. And I just wanted to share that that's a resource. So every topic that you see on my website, I have. Where did the mouse go? My mouse is.
Sometimes you get like a static charge or something. Oh, that's weird. There it is.
Okay.
Oh.
So, oops. So here's all my lecture slides on, like I said, for my IB class. And like I said, these could easily be modified to teach any first-year physics class. I also have my lecture slides for my AP Physics C Mechanics class. So everything from one-dimensional kinematics through oscillation and gravitation. And then I also have assorted labs and other files. So this is just a whole bunch of labs, some of which I have written myself, some of which I have shamelessly pilfered from individuals such as Dan. It's in alphabetical order, not by topic, so you might want to scan through this. All the distance learning labs at the top, so stuff from the PhET site, including stuff we'll talk about this afternoon. Here's my version of the speed of sound lab that Dan took you through with the PVC pipe and the water and the Alka-Seltzer. So my write-up of that is on here. So if you want to see how I approach it. Hopefully nobody is offended by the Comic Sans font.
I am now.
So I just kind of wanted to share that that's what's on my website, so you know that it is available to you and there for the filtering. Thanks, back over to Dan.
You want to start with some white stuff, or you want me to?
Why don't you go ahead and start with the light stuff, and then I'll jump in.
Okay. Let you do the heavy lift. So these are just the ones you're showing, right? There we go. Okay, so light, very prevalent phenomena, but hard to understand. But we all know that light is a, what does that sign say? Well, wave, of course. I mean, oh no, wait. I look a little more carefully. Particle. Oh no, wait, it's a wave. It's a particle. It's both, neither. It's a wavicle. So this sign I had up in my classroom, just printed out 8.5 by 11. And I would have it off in a corner. And I would ask a student who was far away from it to tell me what the sign said. And they would say, light is a wave. And then I would ask a student who was sitting pretty close, do you agree? And they would see, oh, and usually whoever was sitting close to it had seen this before. So they knew, sometimes it took a little prompting. And so it just depends on what experiment you do, what you see. And so in this case, whether you're close or far, I wish I knew who created this sign. I'd give them credit for it, but I don't. I got it a long time ago on the internet. But I had it up in my room for a long time before I noticed that the exclamation mark is a wave and a particle as well. So that, you know, I thought they were a genius, whoever did this, and then that proved it. So that's in the slides. As far as where you would start with light, that depends on what you want to do, your preferences, a lot of different things you can do, but reflection is one of the properties of light that you can start with. And a lot of times people are like, well, just the angle of incidence equals angle of reflection. What else is there to know? There's actually some pretty cool things you can do with reflection without even getting into curved mirrors. And so this one is the see-through box challenge. So I have a little video showing kind of the setup here. So there's my little chick. I can see it. Oh, now I can't. Somebody put a box in the way. Well, my job is to take those 4 mirrors and place them so I can see the box again. And here's the chick on this side, here's the box, I'm here. So I can route the light that's coming from the chick toward my eye around the box with the mirrors. And I actually did this on Twitter because I was doing this for a thing at my job. And I just wanted to see if people could do it without even having the mirrors and stuff. And people did. So would I say this is a remote learning activity? Maybe. And so there's a solution. So if here's the light from the chick, hits this mirror, goes over to this mirror, this mirror, this mirror, and to your eye. And this is what it looks like. And so you can definitely see, the mirrors and stuff. You're not fooling anybody, but you have routed the light around. Another alternate solution, would switch the location of the chick in the first mirror. And if you do that, what you're doing is routing the light coming from the chick going in the opposite direction. And it'll be reversed then because you're on the other side of the chick. You can also do it with 3 mirrors. If you put one of them here and then have this one bounce it here and to here and here. And if there are 3 mirrors, then the image is reversed too. So if you have an odd number of mirrors, the image is reversed, even it's not. I think it'd be much better to have students do this in the classroom with stand-up mirrors. It's sort of like another activity is a laser maze, where students have a target they're trying to hit, and they have a laser that's on a stand, and they arrange mirrors, and they don't get to turn the laser on until they're all arranged, and then they turn it on to see how close they got to the target. It's similar to that, but this one they can arrange the mirrors as they're working on it. It's kind of like a periscope with 4 mirrors, and so a simpler activity would have students build a periscope. And then I'm not going to go into this, but I discovered this one time, this thing called a pseudoscope. And what it does is it routes the light that's going into your left eye to your right eye and vice versa. And it results in some really weird effects. They're not easy to make to work correctly, but I've had students make them before and they worked, well, okay. So I just thought I'd throw that out. If you're looking for something that maybe you've never heard of before, look that up. So that's the see-through box. Another sort of illusion is called Pepper's Ghost. And this relies on the fact that when light hits glass, some of it transmits, but some of it reflects. It depends on the angle of incidence, how much reflects. And so it depends on the material as well, but in general, about 5% of the light striking a window gets reflected. And so I've created this illusion here using that. So we've got a candle there in a beaker. So it's a candle, so let's light it. Now it's lit. Well, it's in a beaker. So we might as well fill it with some water. Oh, it's a special kind of flame. It's one of those cold flames. And if you've ever watched SpongeBob cartoons, you know that you can have fire underwater, and this proves it. Now, if you look at that, there's definitely some clues, especially once it filled with water. We got some odd things happening. But what I did is there's another candle in front of this piece of glass, and I adjusted their positions So the reflection of the other candle, the one that's actually lit, is lined up with this real candle that's in a real beaker. And so this is the setup, and I was only filming this. So first I lined these guys up, and this one I had to put on a little platform so it was the same height as the other candle. You want them to be the same. And then this is the one I lit. And so the flame is being reflected off of the glass, and it's bright, and so its reflection makes it look on par with this candle being lit. And so this is just an aquarium, and I've lined it with black paper. And the candle, if you pour water in, some candles are buoyant, and so it'll come up, and that's no good. And so it's stuck down with a little piece of clay. So it's not something you're going to fool students with. But I guess here's the case where distance learning, you can fool them, right? You could set up the camera so they don't see the whole thing. But in general, you'd set this up in class, maybe have them take some observations or something, and then do the trick with the flame. And do we have the portable one, Tom? So again, the aquarium works really well. That's what I used for many years. But Paul Robinson came up with this sort of classroom version of this illusion that allows you to walk around the room and show students. So we don't need to set it up or anything. So it's just painted black on the inside. It's made out of wood. And we have the candles. And so you can walk around and show the students. Oh, you got a match? Well, sure. Found this. We have this, you could just have it set up like the aquarium. That's the way I did it for many years, and they could just get up and inspect it. But with this, you can light it and then walk around the classroom and show them. Light it.
Let's set it down. Let's see if I have another match. Two more matches.
Uh-oh. To build a fire. Famous Jack London story. The guy doesn't build one and then he dies, Tom. That's okay. Well, poop. We can at least show the water part. So at least we're not trying to fool you, right? So imagine this one was lit, and it would look like it's. They saw the video. It almost lit. So this is called Pepper's Ghost. Pepper was a physicist. And he came up with this illusion, which they named after him. And it's used in a lot of places in theaters to make it look like there's a ghost on stage. But the difference between this and the one I'm doing is the actual candle would be in a level below the table, and this glass would be tilted down toward it. And so you can see, here's the real person being brightly lit, and then this glass is tilted down, and so there's a reflection of them showing in the glass. And so to the audience, they see this illusion. There's nothing really here of the ghost. And if you've ever been in the haunted mansion at Disneyland, in the haunted ballroom, this is sort of a sketch of it. It's a pretty good illusion. There are ghosts dancing around and stuff. How do they do that? Well, underneath where you are when you're observing are these robots, animatronics. Here they are. Here's a picture of them. And so they're moving around. Then there's a piece of glass, and the reflection is bouncing off that towards you. And a pretty good illusion. There's somebody always here keeping an eye on the glass because it's pretty close to people. If you really tried, you could reach out and touch it. And if you get prints on it, then the illusion goes away. So if you try that, somebody will yell at you, at least I'm told. I would never do anything like that. So you can look up Pepper's Ghost. This is from a Wikipedia article, pretty interesting. Some of the stuff more lately with it, they've been sort of reanimating dead musical artists and having them do concerts. And some of those, they're using Pepper's Ghost as part of the illusion. They say they're holograms, but as I understand it, some of them, they're using Pepper's Ghost with that as well. And then I think there's another thing at Disneyland, the Blue Fairy and the Pinocchio ride or something. I haven't seen that one. But anyway, Pepper's Ghost, pretty cool. With a mirror scope. You want to show them that, Tom?
Sure. So these are fun to just have sitting out on your desk. And so I've got a couple of them. So this one has a little froggy. This one has a little piggy. And I'm not sure how much this is being captured by.
It sort of shows. It maybe get closer, like real close. We were doing this for a video at work the other day, and it doesn't have the 3D illusion, but it was showing.
But
you're gonna need to switch so that it's showing on the screen. Because right now we're still looking at the mirror scope diagram.
Oh, okay. That's why it's not showing too. Okay, here we go.
And so it looks like there's a little froggy right here, and I tried to pick him up. It's like, where's the froggy? Where's the froggy? This one has a little piggy in it, and it looks like there's a little piggy right here, and I want to try to pick up the little piggy. And why is it that it seems to be a little piggy there, and there's not? Well, the little piggy is actually down here, and both the floor and the ceiling of this thing is mirrored. Same with this one. And so with this concave mirror, when you trace the light reflects off of the ceiling and then off of the floor and then to your eyes, kind of two things happen. Because of the shape of the concave mirror, it slightly magnifies the object a little bit, so it looks like it's a little bit closer to you than it really is. And the amount of parallax that occurs tricks your eyes into thinking that it is nearer than it is. So between looking bigger and having the parallax, it really seems like there's something right here.
I had one, I made a little button that said press. It was, it had some dimension to it, and it looked like it was a button, and students would go like that. The only thing is they would then hit the bottom and it kind of scratches the mirror up. But you get a real image from a concave mirror if you're outside the focal points. And so what this is doing is taking the light from the object and routing it back toward the opening with these two concave mirrors, and then you get a real image The light is actually passing through that location here, and it has a sort of 3D effect. This is one of the raffle items. I think it's the smaller one. But it does get scratched. But I definitely highly recommend, this is one of the things you put out in your classroom. You know, maybe have a place where you put something out and then you alternate, switch things around, leave it out for a while. It will get a little scratch and it just diminishes the effect a little bit, but. You know,
The kids love it. In years past, when, you know, in the before COVID time, we would do a expo every year, and each department would set up in the gym, and kids would come in and parents would come in and talk to you know, teachers and find out, you know, what should they take next year. And I would like to promote physics, get lots of people taking it. So I would always have one of these sitting out next to a Newton's cradle, and between those two things, kids would come over and just want to play with the toys.
And you also get a nice concave mirror. And so, you know, let's see if we can do this. So you see images upside down. Those are
Aim up.
see it there. And so images are upside down. It's a real image, but if I get closer, at some point I go inside the focal point and it will reverse and get magnified. Did I do it?
Doesn't flip.
If you get really
Oh,
super
if you're
close.
really close.
When it gets really super close, then you can see the scratches on the mirror.
So just even having a nice size concave mirror is good. And it comes with a frog. Or some other creature maybe. You got a pig in that one. You probably added that. So. Okay, some good camera work there. Or the mirror scope. And you can just Google that. You can buy them. There are different size ones. Then we have color by addition. And this is maybe one of the more popular exhibits at the Exploratorium. And the idea is, you know, sometimes they've learned about in art class, color by subtraction. When you add different color paints, you see a different color than you started with. Well, this is color by addition. And so our eyes, and it sort of works on how our eyes see color. We see, this is a simplified explanation, red, green, and blue. And we have sensors in our eyes that can see red, green, and blue. And all the other colors are different combinations of those. And so I have these floodlights. You can still buy these 85-watt floodlights and just a regular old lamp sockets. And you can mount them using whatever hardware you have in your storage room, steal stuff from the chemistry people. I have these, I put a little close up here, these 3-finger clamps. And that's what's on each of these. Oh, the colors look weird there though. It is red, green, and blue. The only thing is your eyes are sensitive, more sensitive to some colors than others. So to make this work, you need to have a dimmer switch. You would probably put it, if you just had one, on the green. The red you turn all the way up. The green you'd want to dim a little bit. What I found, because I had multiple dimmer switches, is I'd put one on the blue as well, and I'd end up adjusting it a little bit. And when you get it all adjusted in a dark room, 3 together look like white lights. But now, if you cast shadows, the shadow of this meter stick is going to look colored because it's only blocking one of the lights at a time. So if I have cyan, I know that I'm blocking the red. And that sort of makes sense. Here's the red light. I have it red, green, blue. And so the Meter stick is blocking the red light from reaching this place, and the other two are making it. In the middle is magenta, because we are blocking the green in the middle. And then over here, we're blocking the blue. So this is red and green, and that's yellow. A little harder to see, but up here are places where this index card I take to the meter stick is blocking two of the lights. And so you can see a red and a blue, and there is a little green, but it's not really showing up. And then where it blocks all three of them, you can usually get that to happen, well, it's going to be dark, right, black. So this is sort of a inexpensive way to make a large color by addition activity. What you could do is have students, you can have them diagram out what is happening. Maybe a black and white sort of image that they would color in, or at least say what the colors are beforehand, and then observe it and see if they're correct. So they sort of predict what color they're gonna see in the place where the red light is being blocked. And Tom has there's a lot of products that are sold that do this. And so Tom has one he's gonna demo here.
See, could we close the back door just to get a little bit less light in here? So this is something I bought some years ago, I want to say from Arbor Scientific. And I've got 3 color spotlights. So I've got my red, my green, and my blue. And so you can show that, for example, when you have green and blue overlap, the result is cyan. When you have the blue and the red overlap, it's magenta. Neither of those is particularly surprising. But then you ask kids, so what happens when you combine red and green light? And they'll usually say, oh, you get brown. No, you get yellow. And again, this has as much to do with physiology as physics. You have red, green, and blue sensitive cones in your eyes. When true yellow light is incident on your eyes, it stimulates the red and the green cones. So you can trick your eye basically into thinking you're seeing yellow light by shining green and red at the same time. And then if you shine all colors at once, so if I overlap all 3 of them.
That's the hard thing, is to get it to look, it's looking pretty white on the video, so that's pretty amazing.
And then you can make your shadows with different colors, which is kind of cool. Another thing I will do is kids will walk in the room and I might have something like this on the board. 1 second. Let's see what my spot is. And they'll look at that and they'll be like, well, that's not my favorite team. They're like, oh, I'm sorry. How's this? Is it showing up?
It's almost the green is too bright there. Here, it works for me.
So now I can, and we go and talk about reflection and then why you see different colors.
Turn the intensity of the green down. There you go. There you go. That means
So there you can see what it's like. Well, if I turn all of them on, that's still too much glare.
here in the classroom, it looks a lot better, but some of the other things were working better on the video.
So black ink, green ink, red ink. And the other thing I like about doing the demo this way is not only does it help your students learn about color, but if you need to summon Batman. One other thing I like about this is that you can swap out the filters. So right now I have red, green, and blue filters, but I'm going to turn off the red and the green, and I'm going to swap out a green filter for a yellow filter. because this is the one that gets students the most. So here's, I've got yellow light, I've got blue light, and of course, when you combine yellow and blue make white. And like, wait, where's the green? It's like, this isn't paint. And so this, I think this in a very visceral way shows how blue and yellow light add differently than blue and yellow pigments do. And this is also a chance for me to plug my alma mater coca.
So there's all kinds of things that will do this. We used to, let's just demo this. Yeah, sure.
So here, this is from teachersource.com. This is just a little ball. Actually, this is working pretty well on the video. So this looks fairly white. I would say it's a little flickery. But if I going on is there are 3 LED lights in this thing, red, green, and blue, each one turning on and off at a frequency of something like 40 hertz, which is faster than the human eye can follow it. But they're turning on and off out of sync with each other, so it goes red, green, blue, red, green, blue, red, green, blue. Our eyes can't process information that quickly, so the red and the green and the blue signals are sent to our brain simultaneously, and it appears to be white. But if we move this thing fast enough, and it also looks very trippy when you just wiggle it in your hand. This is also handy even when I'm not covering light, but if I want covering centripetal force, this is just a handy thing to talk about centripetal force, tension in a string is an inward force. I'll use that then. I also have a Doppler shift one where that one's over here. So I have a little speaker here. This is not very loud, but it sounds like a constant tone to me. If I twirl it like this, students perceive the Doppler effect. They can hear the pitch go high and low as the ball goes toward them and away from them. And then I ask them, do I hear the Doppler effect? And they have to reason out, no, I don't, because it's never heading toward or away from me.
You don't hear any though, because you got 2 ears and you're not centered on your ear.
No, I kind of hear it now, but it's hard to pay attention to because I'm too frightened of hitting myself in the face. So very useful.
And it's one of our raffle items. They're from teachersource.com. We used to hand out a different one too, and this is what that looked like. Oh, that looks so cool. I think I'm at a rave. So those were called light sticks, and they are doing a similar thing to the ball, but it was a white foam stick. They also had the LEDs in it. Similar item. And then also you've got colored lights on any screen you use, right? But you don't normally perceive that because they're very, very tiny colored lights, but they can be revealed with a microscope. I used to use a handheld 30 power microscope that worked pretty well, but it's real easy to turn your phone into a microscope. So if you look online, and it's going to be Amazon, right? But there are other places you could look. But if you search magnifying lens for cell phone or for phone, you'll find all kinds of things. Some of them are just like $2 or $3, and they attach over the lens of your phone, and you can zoom way in. There's some that go, if you go real far, you'll need a light source. So there's some that come with a light source. I'm not recommending this one here. I just have to grab a picture of it just to show you. It just clips over the corner of your phone. over the lens, and this one had different powers. So those work really well, but once I was showing them at a workshop and somebody said, hey, I just took the lens out of a laser pointer. And I don't even know if I knew a laser pointer had a lens at the time. And I always had laser pointers that were not working, but for some reason I just didn't throw them out. And so I went and got one of those, and I took some pliers and a little bit of effort, but I ended up with this tiny little lens, and I could add a little piece of tape on it and tape it over the lens, and that's what I took these pictures with. And so you put it over the lens and you zoom your phone all the way in, and I looked at I made a square in Microsoft Word and filled it with red. And this is what it looked like magnified. And then I did green, and then blue, and then white. You can see all three are on. And then yellow, to my eye, there was this brilliant yellow square, but to the microscope, it's just red and green lights. And there's just something disconcerting about that. You realize that you're not really perceiving reality with your senses. We're only getting a version of that. And so it's very disturbing. And then cyan and magenta as well. There's something about the yellow that just gets you. And so I recommend doing something like that. Depending on the resolution of the screen, even a regular magnifying glass will show it. The old TVs definitely were easy to see. Some students have noticed this when a drop of water gets on their screen, it'll act like a magnifying glass. And you can see this, just not quite as magnified. But just put a little drop of water on the screen works too. And even a drop of water on the lens on your cell phone works, but not as well as a solid lens. I recommend trying that out. And then another way to study the spectrum is to project the spectrum with an overhead projector spectroscope. And Tom has old school one here. Do I set this up?
Sure.
I don't want to mess it up. I can make this slip.
Clipboards. Desk.
We want to get rid of these old overhead projectors. It might be too late for you. Maybe you can find one on your campus, but this is the best way to project the spectrum in the class. So Tom is putting a piece of grating over the projector side. And so this is a piece of diffraction grating. Holographic diffraction grating works the best. And if we turn that on, well, I see a little hint of color here and there, but the problem is it's overlapping color. Oh, we have it.
Oh, I need to rotate it.
Well, it works, but usually have it show on the side.
There we go.
Is that showing well? Oh yeah, real well. And so you get this really vivid spectrum. Roy G. Biv. You don't have all the filters and stuff, do you, Tom?
No.
I think I left that in E-Tech. And so I think that's where all that stuff is. But that's all right. We'll just show this part. So you get this vivid spectrum. You have a yellow highlighter, maybe?
I believe I do. Yeah, right by my Kleenex.
I can do at least, well, maybe one of the demos. So we have the visible spectrum, red, orange, yellow, green, blue, not a lot of blue, right? Sometimes I see a little turquoise in there. And then violet, but Newton named indigo in here. Now, people perceive color differently. There are definitely different things going on in different people's eyes. You can study it. So maybe Newton really saw indigo. The general belief is Newton also was into biblical prophecy and occult sort of things and numerology. And to him, 7 was a special number, and he wanted there to be 7 colors. And so he came up with indigo. I would have had turquoise, but then it's not Roy G. Biv then. It's Roy G. Stuff. So we know there are colors beyond this, or wavelengths beyond what we can see. There's infrared here. We'll talk a little bit about some infrared things you can do later. But there's some ultraviolet here. Not a lot coming from a tungsten filaments through the glass and stuff, but there's some. There's a way you can show it. I have a fluorescent highlighter here on this piece of paper. And it is fluorescing because I have it in the violet part. High energy light hits the material, excites electrons to a higher energy state. Now, if they just drop straight back down to their ground state, we wouldn't see anything. We'd see purple, right? But we see a different color because they're taking intermediate steps down of lower energy. And so in this case, giving off the green or yellow, whatever you want to call that color. But my question is, this only works in a dark room, maybe it'll work on camera or not. When do you see it first start to glow? So as I bring it in, we're getting a little sunlight in here too. But it usually starts to glow. It is glowing, but I think some of it's scattered sunlight. But
Let me try closing the door.
well, maybe, yeah. So it's a glow about there. So it's not quite to the violet yet. It starts to glow, and so some of that is the UV coming from the tungsten bulb in the overhead. A couple of things about this. So tell me if I blind you. But you can see we have this slit, right? So you don't need this huge piece of grating. You only need a piece about this big. And so you can just get a, I use an index card, and then cut a slot in it, cover that with grating. But if you have a big piece, that makes it easier, just put it like that. And that will be one of the raffle items, is some grating, and we'll talk about some other things you can do with it. Yes, light stuff is hard to do remotely. That looked pretty good. Both those things did here. This almost looked better remotely because it was saturating the camera. And so this is just a slide showing you how to do it. You can see what I was talking about with the index card. That's all you need is that amount. And then Tom had 2 clipboards. Just anything opaque. I used black cardstock, and then adjusting the slit width will adjust the brightness. So if you're having to do this in a room that you can't darken very well, a wider slit will make it brighter, but the colors aren't as separated then. There's some overlap. And as you make it thinner, they'll get a little more defined. But I found whatever room I'm in, I'm always able to come up with something that works pretty well. And this one, I don't have the stuff here. I'll just throw this out as an activity. It's very well described in the handouts. And so this was an exploratorium activity that involves using a mag light. You don't have to have a mag light, do you? had one in my cubicle, and I was looking at it and didn't. So what's cool about mag lights, I can just do it on the camera here, is they don't work. Yeah, these are LED ones. They don't have the candle mode. Oh, that's terrible.
I thought they did. One might be dead. Try and spring that one all the way.
That's pretty. Oh, there we go. So they have a candle mode. So I took it completely off, and then this acts as a little holder. And this is an LED one. For this activity, I recommend the incandescence, but this might work the way I'm looking at it. I just never tried it. And you shine it through perf board, which is just a piece of material with a bunch of little holes in it. And you tape it off so that you have a grid. I think when I do it, I do 8 by 8. And then it projects onto a piece of paper, and you move this piece of paper further away and count how many of these holes show up in the square. And if you measure the separation and the number of holes and do a graph, you get an inverse square. That's not explaining it very well, but again, this is the handout in here, and it's a version of the Exploratorium one. The Exploratorium took down this version. I'm not sure why. Maybe the perf board industry ticked them off or something. And so I fortunately had archived it. But the other way, they just shine the light through a square hole, and then you measure the area of that hole on some graph paper, and then move the graph paper away. In that case, the number of squares goes up. And so it's a great activity. I would do it if I taught math or something. But in physics, we're thinking of gravity, right? Or electrical force, or the intensity of light, and you want it to go down with distance. And in this case, counting how many holes show up in this little square here, which is the same area as this, works pretty well. You can do it in a fairly well-lit room. And again, if you're looking for an activity like that, go look that part up. So the coin and cup, take some skilled camera work here. Do with okay. What we want you to do is look down on it. Let me get the not live yet. There we go. So I just have a cup with a coin on the bottom. I put a little piece of clay under the coin so it doesn't move around easily. You could, I don't know, make a little wad of masking tape or something. You want it to stay put because I'm going to be pouring water in there. And so Abigail is holding the camera so she can see the coin. And what she's going to do now is slowly walk away until the coin is being blocked by the edge of the cup, but no further. Just go only as far as you have to block. Maybe go a little closer, start to see the edge again. There, okay, there. So now she can't see the coin, but by pouring the water in, she can see it now, and she did not move, not 1 millimeter. And so it's kind of a cool refraction demo. There you go. That was very good. And so not easy to do. So definitely you could do this one with distance learning, right? If you have if maybe somebody have a document camera at home, what a lot of people are doing is using their phone, but you can get a box and cut a little hole in it and put your phone on top of the box so it's pointing through that hole. And then whatever you put under it, it's like a document camera. And so you could do this with that. So this was originally Abigail looking, or you as well with the camera, looking, you could see the coin. And then you move back. And so that light that was hitting your eye is not hitting it now. And when we fill it with water, this light, when it comes out of the water, bends toward your eye. So now you can see it. What I would do with students with this, since it's such an easy demo that anybody could do it, is I would do it for them, have them sketch this. It's kind of hard for them to do this on their own unless you've really covered refraction well. Usually this is an intro activity. But then I would ask them to demo it for somebody else and explain to them with their drawings what's going on. So that's, I think, where the learning would occur, not in just the demo. And so there's a write-up of this here if you want some more information on it. Back in 2017, when we had the total eclipse, I went up to Madras, Oregon, Madras High School, where Lowell Observatory was putting on an eclipse event with the Science Channel. And I was working with another teacher to do activities and demos and stuff for the people who were attending. And we wanted to do some sort of demo showing how, you know, the most famous total eclipse was the 1919 one, when they confirmed Einstein's prediction that gravity bends starlight. So the gravity of the sun makes the light from stars bend in a similar way. It's not the same thing as refraction bending light. And if you could, this isn't what they did, but it would work this way. So imagine there's a star on the other side of the sun that is just barely blocked by the edge of the sun. Well, during an eclipse, the light from the sun gets blocked by the moon, and you would be able to see the star because its light would bend around the edge of the sun due to gravity. Refraction does something similar at a sunset. So when you see the last bit of the sun sinking into the sea or wherever, it's actually already set and is already blocked by the edge of the earth. But refraction of the atmosphere, having to do with the variation in the density of the atmosphere, bends the sunlight towards your eye and you can still see it. And so what we wanted to do is just to make this point, do this coin and cup activity with a large group. So we have, well, I'll just show it to you and then explain.
Stay in the same place, and you'll notice that you'll start to see the light even though you didn't move.
As the warpage increases.
Exactly.
That's cool.
And
Yeah.
so that's
So let's
stay in the same place.
So instead of a coin, we have, and when I first came up with this idea, I was going to make an LED light that would work underwater. But just for the heck of it, I'm like, well, maybe there's something like that. There's tons of things like that. It's like a whole industry. They even work by remote control, and they're pretty cheap. I got like 12 of them for $20 or something with the remote control. So there's an LED light in the center of that bucket, and we have a whole ring of people around it. So you could do this with a class as well. And I had to move back until the edge of the bucket was blocking the lights. And then we would pour the water in, and miraculously they could see the light then. And what was cool is you could see that they could see the light because all of a sudden their eyes would be lit up by the LED light. So successful.
You'll notice that you'll start to see the light even though you didn't move.
As the warpage increases.
Exactly.
That's cool.
So those
So
are
that's
some high school kids, so we sort of went through our shtick with them, and they learned it very well, and they did that demo, I don't know, dozens of times, and were very good at it. Very, very dramatic. What I changed about this, I've since done it in workshops and things, is I got a
stay in the same place, and you'll notice.
So the fact that the light is leaking through the bucket, I thought was a little distracting, and a opaque, a black bucket worked a little better, I thought, but this worked just fine.
You can get both a bucket and an LED light at Dollar Tree for $1 each.
There you go.
You want to put the light in a baggie or something, but
So the submersible ones, they're at the Dollar Tree. So, but they're called submersible LED tea lights. If you're looking for doing a big version of it. And here's definitely something you could do with distance learning. Tom's going to show an actual thing of this. Maybe have you do that now, and then I'll show
Sure.
this. So it's just Snell's law of refraction. So you have that out.
So this is another handy little gizmo brought to you by the fine folks at Arbor Scientific. It has a cat here on it. So it has a little laser, and you can set the laser to point in any direction, 360 degrees. And so you can use this to illustrate the fact that the light is bending when it goes from air into, this case, water. And I go into more mathematical detail, go into Snell's law, and we predict, okay, if I shine it at 50 degrees, what's the angle that you would calculate if you have the known index of refraction of air and water? And then in this case, it looks like it's about 36 degrees is the angle of refraction. So then I can switch it around and say, well, what if I'm starting in the water at about 36 degrees? Oh gosh, about 50 degrees. So any ray can be reversed. Whenever I try to convey the idea that any ray drawing can be reversed, I ask students, so what does it say? Sometimes on the back of a big rigged truck, if you see a sign on the back of the truck, and kids will usually say, how's my driving? I'll say, other than that, if you can't see my mirror, I can't see you. So if there's not a line of sight from you to the driver of the big rig, there's not a line of sight from the driver to you. So they might slam on the brakes not knowing that your little car is about to be crushed. Then we can go a little step further and say, okay, if you start in the medium where the speed of light is slower, then the light is going to speed up when it exits, in this case, the water, and goes into the air. When you have part of the wavefront in the air, part in the water, the part that's in the air is going to speed up first, and the beam is going to pivot until the whole thing is in the air. So the angle of refraction is going to be larger than the angle of incidence when you're starting in the medium with the larger index of refraction. And then if I tilt this up, we can eventually see that there is, once I go beyond the critical angle, then I get no refraction, the light totally internally reflects. And then I can also demonstrate that with a laser pointer and an acrylic pipe. So this is how fiber optics works. So light is incident on one end of the optical fiber. In this case, this is a pretty thick optical fiber. It's just a piece of acrylic twisted into kind of a pretzel shape. And if I shine my green laser into it, it might help to turn the lights off. But if this was utterly perfect, flawless, transparent material, you wouldn't be able to see the light other than coming out at the other end, but this is, it's got little flaws in it, so that means you can see the light actually bouncing around, totally internally reflecting each time, and then eventually exiting on the other end. So this is how optical fibers work. So I like to show this to students, and I have this little desk lamp where it looks like, not to quote a former president, but it looks like I have 1,000 points of light right here. Well, I only have one point of light, one light source on the inside, and that light source is sending light into all these, hundreds and hundreds of little fibers, and that light just totally internally reflects down each little optical fiber until it gets to the other end. So what I do for a lab with this material is I do a lab where first we take a substance with a known index of refraction. So in this case, I have some frosted acrylic. Good for the physics lab, terrible cereal. And students shine a laser into it, and because it's frosted, they can see the laser inside the material. Now they do this not holding it in front of them the way I am, but on a piece of graph paper, and they graph out where's the origin of the laser, where does the laser enter the acrylic, where does the laser leave the acrylic, and measuring the angles and setting up Snell's law, they can determine what is the index of refraction of acrylic, and it turns out it's around 1.5. So they do that, and that shows that they know how to calculate the index of refraction of a material. For part 2 of the lab, I have made a class set of Jell-O molds, and I use these little semicircular shaped dishes I got from, again, Arbor Scientific. And so now they have to repeat the procedure, but shine the laser into the flat end of the Jell-O and measure the angle of incidence, measure the angle of refraction, set up Snell's law, and calculate what is the index of refraction of Jell-O. And unlike acrylic, every textbook I've ever thought of has a list of, index of refractions of common materials, glass, water, diamond, quartz, etc. I have never taught out a physics book that on that table it included Jell-O. So that's not something that they can look up to sneak the answer to, but golly gosh, if it doesn't turn out that the average results they tend to be is right around 1.32, 1.33. And that's because what is the main ingredient of Jell-O? Water. I find that yellow Jell-O works the best if you're using red lasers, which is what I have the students use. Orange Jell-O works okay. Green and red are terrible for this, so go for the yellow Jell-O. So that's what I do, and the write-up for this is on my webpage. I think I called it Lab Snell's Law. But there's also a write-up on my webpage for a distance learning version that uses the PhET website. I think that's what Dan was going to talk about.
So I think we're coming up on lunch. And so, Belle, you want to tell them about lunch, and we'll be coming back at 1.
Okay, along with me being the PTSOS person, I am also the president of the local professional organization called the Northern California and Nevada section of the American Association of Physics Teachers. And we have 2 conferences a year. Our spring conference this year, April 24th, it's a Saturday. It's free. So since we can't meet in person and there's no membership fees have been suspended, conferences are free, so it is no cost to attend. I'm going to post this link in the chat once I'm done here. Speakers. So we have Desiree Whitmore from the Exploratorium and Ada Bemard from Caltech.
Laser check?
I don't know. So Desiree's talk is titled "Who Does Physics? Exploring Representation in Physics Class." And Ada's is "Fostering Young Scientist Identities Through Diverse Representation in STEM Education." So those will both be, I'm sure, very stimulating, interesting, amazing talks that will dovetail together beautifully. And we're still have the same usual share and tell we always have. We'll have breakout sessions. We'll have an extended lunch with lunch breakout sessions. Again, it is Saturday, April 24th, and it is going to be over Zoom. And our hope is that next fall, we will be back in person. I believe at Foothill. I'm not sure. I'm not entirely certain. But our hope is that in November, our next conference will be in person, and we will keep you up to date on that. If you need help with subsidizing childcare or other family obligations, there is an application for that as well, where our organization will help subsidize childcare for people who need help attending the meeting. And I think that's all I have to say. If you have any questions, you can shoot me an email at the same, theptsos@gmail.com. And I think it's going to be a good time. So I'm going to stop sharing. I'll put the link in the chat. And then I will go back to being quiet and creepy in the background.
Ready? 1, 2, 3. Hi, everybody. Welcome back. So we were talking about not diffraction. That's later. Refraction. And so mentioned finding the index of refraction of Jello. I'll turn this off.
So there's something that the security setting needs to be, so some people can't start videos and some people can't do some other stuff. So there's some, I may have messed some things up when I was setting things up for lunch, but
we can take time to make sure, so they can't.
I don't have access to make the changes because I'm not the host.
Okay. And so.
Otherwise I just do it.
What? So am I back to?
It's gonna be under security.
I just wanted to make sure, okay. So what are you, I mean, when they can't see the screen, so the screen's not being shared?
They can see your screen, but they can't turn on their own videos.
Okay. Why do they need their own videos?
I don't know, they just asked me for it.
I mean, we should fix it, but I'm not really sure how to do that.
Go back to the main Zoom screen.
Security.
Yeah. Allow participants to start video. So just click start video, I guess. I don't know why it was unclicked. Should work now, I think.
Otherwise, I think everything's.
Alrighty. Well, so talked about measuring the speed of light in Jello as a hands-on refraction activity. For distance learning, there is a PhET simulation where you can turn on your laser, shine it at any angle and you want to. You can change the. Right now, we're going from air into water. I could go from glass into water. I could go from air into mystery A. And there's a protractor tool that lets you measure your angles. One thing that's kind of cool that the simulation lets you do that you can't really do in person is measure the intensity of both the reflected portion of the beam and the refracted portion of the beam. So that's an investigation. You can add something to what you could do in the
I like how you put the water on top of the air.
So yeah, you can do all sorts of stuff. Here's water, here's air. So notice, oh, I got total internal reflection going on here. So I have a write-up for this that is also in my files. Just want to share a few other. Actually, before we leave the topic of refraction, you want to show your demo with the fish tank?
Oh, might as well. So Tom was showing that great thing by Arbor, where you can see the laser beam going into the water and coming out. Otherwise, you have to kind of, go to some great lengths to do that. It's better to do this with an aquarium, but this was, Tom had fish in his, so I use this one. So I've got a mirror in the bottom of this. I added a little bit of mop and glow.
I think it's still looking at me.
Oh.
Or am I on the
I'll
web
go to
page?
QuickTime, so along the bottom.
Oh, I see. Okay. Oh, is this what people are seeing?
Yeah, that, well, it is when we do
I
that.
think I might have stopped sharing. Hold on a second, let me start sharing. Yeah. Do I want to share whole desktop?
Yeah, that's what I've been doing.
Okay.
And then whenever you want to show the,
Okay, there we go.
whenever you want to show the widescreen, just hit on the QuickTime down
There we
there.
go.
So you, so the mop and glow added to the water really makes that beam visible. And except you can't see it coming out. The Arbor thing had it so the laser beam was lined up and kind of skidded along that white background. But this atmosphere aerosol
Nope. There you go.
or fog in a can, Arbor sells it. We used to just hit chalkboard erasers together, but those days are gone. Here, you spray it.
Hold on. I'll get this wider. Okay.
There you go. Also, if you're, breaking into a bank vault and they have a laser maze security system, that stuff helps you see it. That's good enough. Fog up Abigail. So just wanted to show that real quick as another alternative, but I really like this geometric optics experiment thing that Tom showed. Oh, and lasers are part of the raffle. We have red, green, and violet. And we'll probably let you pick 2 or something like that. So you will have lasers.
I just wanted to share a few more of my slides that I have. So we'll go to, so I've broken up light into light as a wave is one set of slides, reflection and refraction is another set of slides, and then we'll get to diffraction and interference later. I just want to hit a few highlights from these. So this is the lesson 4D. I wanted to share, this is my take on the woman yelling at cat meme. So for all, is light a particle or a wave? Yes. So like I said, I go through a lot of lecture material with the students.
I hate to be Captain Bill like that woman was actually under some severe emotional trauma at that moment.
Gotcha.
And not just like a woman throwing a fit about nothing. So that's one I don't use anymore. Other people can make their own choices, but that is.
I want to second that and say that we present such few women in physics that presenting them as hysterical when they do come up definitely brings up something for me.
Gotcha. That is definitely good to know. So I go through a Romer measured the speed of light, Michelson measured the speed of light. What I want to get to is this is one of my favorite things called polarized light. And this is something that's very fun to teach. So let me, again, another thing that you never want to throw away an overhead projector for.
I saw they were making fun of this in the chat, Tom. They're like they still exist.
So let me. So now how do I go back to just going from that camera?
So you have it on presenter. Started to show you this and I got distracted. So you go click on quick time. Okay.
Yeah. So let me grab a couple of my polarized filters. So I have a single Polaroid filter and I put it on my overhead projector and rotate it. I don't really see much happening. It's blocking some of the light, but the angle that it is rotated to doesn't really seem to influence how much light is being blocked. And that's because the incandescent bulb inside this projector is a unpolarized light source. So what do I mean when I say light is polarized? So light is a wave. It turns out it is a transverse wave. And when you have all of the waves in a particular light source vibrating in the same direction as each other, then we say the light is polarized. So if each of my arms is a photon, here's some polarized light. So they're both vibrating in the same direction. This case up and down. If they're both vibrating side to side, this is also polarized light. Now, if I want to impersonate unpolarized light, that takes a few more motor skills. I have to have one vibrating up and down, one vibrating side to side. So this would be unpolarized light. So if you have a Polaroid filter, then what is going on is you have light that is trying to pass through molecules that are very long chain polymers, and they're kind of stretched out and oriented so that the spacing between molecule to molecule actually acts like a little slit. So if I have, let's say, a single filter, and I send light through it that is unpolarized, some of this light is going to be vibrating side to side. Some of this light is going to be vibrating left, up and down, side to side. Some of it at an angle. Well, the vibrating up and down is oriented with the slits, so it's going to make it through just fine. Vibrating side to side, perpendicular to the slits, it's totally blocked. Vibrating at an angle, the component that is vibrating parallel to the slits makes it through. And if my light source is unpolarized, it doesn't matter the angle. What if I now put a second filter? Well, it depends. Is the second filter lined up with the first filter, or is it at an angle? So if I put a second filter on top of the first filter, I'm going to hold this one steady. Oops. It keeps drooping. So notice it goes dark and light and dark and light. And so when it's at its darkest, that tells me that the second slit is perpendicular to the initial slit. So whatever makes it through the first one is blocked by the second. So now is when I throw it to students is so right now I have two filters totally blocking all of the light. Is there any way I can add a third filter without changing the orientation of the first two, but allow some light in. And I don't answer right away. I tell them, turn to your neighbors or turn. I'm going to put you in a breakout room for a minute, try to figure this out. And they usually figure it out that if you add a third filter in the middle, if it has its little molecular slits at an angle, then the component that's at an angle gets through here, the component that's at an angle gets through here, and then here I don't have any horizontally vibrating light, but here I do, and now a little could get through. Let's see if that actually works, and let's see if it's actually picked up. I've got 3 filters now. It's a little hard to tell when you turn off the lights. I don't know if you can pick this up or not, but there's 3 filters here, and some light is coming through. Not a lot, but a little light is coming through here, and no light is coming through here. So it's just kind of counterintuitive and paradoxical. You have 3 filters letting some light through, 2 filters not letting any light through. And I'm feeling an urge to go spend money with a MasterCard. Or make a Venn diagram, either way. The other thing I like to show about polarized light is that's how modern 3D glasses work. You know, in order to perceive something as 3-dimensional, your left eye and your right eye have to see different things. They used to trick your eyes into doing that in, old, 1950s horror movies with the red-blue. But I don't know about you, but that always gave me headaches whenever I tried to watch one of those. It was very jarring to have a strikingly different color in one eye than another. Modern 3D glasses don't use 2 different colors, they use 2 different polarizations. So when I went to the movies a while back, I think it was when I went to see the first How to Train Your Dragon movie, I asked if I could keep my glasses for education reasons, and the theater said sure. So if I put a filter over one of the lenses, well, it looks like it's letting light through just fine. Oh, but until I turn the filter, now it's not. But now if I just slide the filter over, now it's not blocking out the other one. So the 2 lenses in a modern 3D glasses are polarized, but they're polarized differently to each other. So one eye is seeing, for example, a vertically polarized image projected on the screen. The other eye is seeing a horizontally polarized image on the screen. And that way your left and your right eye are seeing slightly different things, and the images are calibrated so that when your eye sends both signals to the brain, it processes it as 3-dimensional information. And the nice thing is when you then are just wearing them and just looking at the world, it's just kind of like wearing polarized sunglasses. It's not jarring the way red-blue is jarring. The only thing is, let's say you're at the movies and despite the fact that it's 3D, maybe it's not the best movie in the world, you get a little tired, slump a little bit. And eventually, it's going to get to the point where now, instead of 2 sharp polarized images, one in left eye, one in right eye, now you're letting components in of both, and you're seeing kind of a blurry image. So the important thing is, if you're ever going to slouch in a 3D movie, slouch symmetrically.
I run into that every time. I learned that I watch movies like this.
Yeah.
And I just be like, what? Oh, over and over again, every time.
So there's a whole activity I like to do with students in polarized light, investigating different basic substations, different surfaces. Do they reflect light or not? The activity is called Shades, and it's based on something that Paul Robinson wrote for the conceptual physics curriculum. I kind of did my own write-up of it, and that's on my website. I'm going to go to my reflection stuff. me skip ahead to this question I like to pose to students. So if you are looking at yourself in a mirror and back away from the mirror, what should happen? So here are the choices. You see more of your reflection. You see less of your reflection. You see the same amount of your reflection. You see yourself winning the Quidditch Cup. Or you're a vampire and this is a trick question. Well, we can guess, and students will guess, and they will often guess wrong. Or we can use some geometry and figure it out. So I found this image of this dapper looking gentleman on the interwebs, and I wanted, basically I wanted somebody wearing a tall hat just so that I could draw arrows that weren't too squished. So if he wants to see the top of his hat, he can look at the top of the mirror. If he looks at the bottom of the mirror, he can see about halfway down his thigh. And that's when he is this distance away. So he can see from basically the upper part of his leg to the top of his top hat. If he backs away, looks at the top of the mirror, he sees the top of his top hat. Looks at the bottom of the mirror, he sees about halfway down his thigh, and he sees the exact same part of himself. So the correct answer was you should see the same amount of your reflection. And this is something that stymies students. They swear that's wrong, that if they back away from a mirror, they see more of themselves. And I explain, yes, that is probably true. If you're in your house and you're looking in a large mirror, what room are you probably in? You're probably in your bathroom. Well, what else is present in the bathroom between you and the mirror? Your sink, your countertop. So if you back away, it's in the sink and the countertop is not in the way anymore. So it's not that your distance from the mirror that is important so much as, is there something in the way? But if you just have a mirror on the wall, then you should see the same amount of yourself. And for students who just won't believe the geometry, I have a mirror that I mount on my wall. So let me switch over. Choose slides. You do that, you can still get everything. So I just mount this little square foot mirror on the wall, and I can ask for a student volunteer. So I have them come and say, stand about a meter from the wall and show me with your hands how high you can see, the top of yourself you can see and how low you can see. And then I say, okay, if you back up, you expect that to get wider or smaller to stay the same. I say, okay, now back up, and then they back up. And golly, if you don't see the same amount of yourself. And students won't believe me, and then they'll come up here and they'll do this, and they won't believe their own eyes. And I always like to leave a few minutes to get into class so that everybody has a chance to come on up and do this. Now, it's usually at about this point that I pause and I say, now, I'm about to teach you something now that is not going to be in a physics book and isn't something that I think, the man wants you to know, but I think it's important that you are taught the controversies and you're taught the alternative explanations and that you can decide for yourself. I have an alternative explanation for mirrors, and it has nothing to do with, flat surfaces bouncing light off of it. Here is what I would like to put forth to all of you. That every mirror you encounter is in fact a portal, and that portal leads to a parallel universe that is identical to ours with two exceptions. In the other universe, left and right are switched, and that universe doesn't have any vampires. Let's explain that using the law of reflection. I think, other than diffraction stuff, I think that's all I have on light.
Okay. I found students though don't know the vampire myth because of those like vampire books and movies where they could see their reflection. They just don't know that mythos. But you can still tell them that.
Folks have a couple questions about doesn't have any what.
What's that?
So somebody has a question that doesn't have any what?
Vampires. Because vampires can't see their reflection. So when one of our vampires looks in a mirror, they don't see anything because there's no vampires in that parallel universe.
But you say, but they might say, well, why does a mirror feel, it's supposed to be a smooth surface? It feels like a smooth surface to me. And it's like, yes, of course, because you are exactly lining up molecule for molecule with your counterpart in the other universe. So of course it's going to feel smooth.
Okay, so here we are. So just a few more things you might consider trying with your students. This one you definitely can do. When you talk about converging lenses, convex lenses, and you talk about image formation, they clearly see when they do the ray diagrams or see the ray diagrams that the image formed is upside down. And then they learn that in their eyeball, in the human eye, is a convex lens. And so the images that your eye is forming on the retina are upside down. Well, I think the first time somebody hears that, that's kind of hard to swallow, similar to the mirror thing, that as you move away, the amount that you can see stays the same. So convince me. Well, there's the ray diagram. That's all we need to show you. Well, maybe there's a way we can show it. And there is. So if this image is being formed on your retina, there's got to be some way to sort of bypass the lens. How can we get some light to the retina without going through the lens? You can go through your mouth. And so I used to do this with just a flashlight, and I won't do it because it's Tom's flashlight, but a bright flashlight, if you stick it into your mouth and shine up, your head is filled with soft tissue, and that light penetrates it, and you get a red glow on the retina from the light that's kind of sneaking in behind the lens.
You do have to get way back behind the hard palette though, like almost gag yourself with a flashlight.
I don't know about way because it bounces around and stuff, but I haven't, I'd say if you're easily gagged, that might be a problem. But I haven't seen that as an issue for most of the people.
With cell phones, it's because the light is so small.
Well, it's on the corner though. So again, I've done this with a lot of people.
I mean, I
Is
just did it with my
everybody gonna,
flashlight.
so.
Yeah.
So if you get that light up to, so I used to use really bright LED flashlights, but you're not gonna pass that around the classroom, especially now, and have students all stick the same flashlight in their mouth. And so somebody once said, well, have you tried it with a cell phone? And I was like, well, no. And so we did, and it works just fine. The key thing is you need to dark adapt first. So if you are going to do this with students, have some stuff you're going to talk about, have the lights in the room down. 5 minutes should work, but again, everybody's eye is different. So I've done this with a room full of 100 people before, and most of them saw it. Some didn't, and I encourage them to try again later and really go for the dark adaptation. But what's cool is you see this red glow, and it's coming from below your eyes, but the red glow that you see is on top. And so you get the sense that your brain is flipping that image around. So the light, it looks like it's coming from above you when you're shining it clearly, there's no doubt about it, from below your eyes. And it's a pretty eerie feeling. Again, some people it may not work with, but in my experience, most it works with. So, the other thing that helped people that were having trouble is I had an LED with a flashing mode, and then they could see it blinking, and that helped. And with your camera, well, take a picture of the upper part of your mouth. And so when the flash, and turn it on flash, so when the flash goes off, that might help as well. So definitely give that a try later, or I guess if you're in a dark room now, you could try it. Another activity I mentioned, when we're looking at the spectrum, we got some evidence that there's ultraviolet. How about infrared? Well, you can repeat the experiment of William Herschel. So William Herschel was a German immigrant to England, and pretty much adopted England as his native country, and was a very accomplished scientist, as was his sister Caroline, who lived with him. He discovered the planet Uranus in 1781. Well, some teachers get a little uncomfortable with the fact that there's a planet called Uranus. There's all the chuckling and stuff. Well, Herschel named it George. So he's not to blame, because George was the king of England at the time, and he thought that would be a good thing to name it after his king who was sponsoring him, and he'd get more funding as a result. But the international community just didn't go for that. They didn't want it to turn into this political thing, and so they settled on Uranus. I kind of thought it'd be good if they kept that and just always name planets for the king of England. Pretty sure when Pluto was discovered, there was a King George then. So we'd have two planets named George. Well, then they deposed one of them, huh? And so he discovered infrared in 1800 with a pretty elegant experiment. He was interested in how hot or how much energy were in the different colors of a spectrum. And so he has sunlight passing into a room through a prism, and dispersion spreads it out, and he would place thermometers in the different colors and measure the temperature change over time. And being a good scientist, and that's what this picture is showing, he didn't only do that, he also put the thermometer outside the visible as sort of a control. And to his surprise, that one actually had the biggest temperature change. And so he realized there had to be some sort of unseen radiation coming from the prism, ultimately from the sun, that was below the infrared, or below the red, so infrared. And this is the actual prism he used from the museum. So how would students do this? Well, it sounds pretty simple, right? Prism, sunlight, thermometer, but it's pretty hard to get good data like that unless you have a setup like Herschel did inside a room with sunlight coming in. But NASA came up with a pretty good way. This was done as an activity for the infrared space telescope, the Spitzer space telescope. And so they we have a copy box here and a glass equilateral prism. It has to be glass. The plastic ones absorb too much of the infrared. And you cut just a little slot in the box so that it's a little smaller than the prism, so it sticks there. And the sunlight casts a spectrum into the bottom of the box. And then you have several thermometers, 2 or 3 works. And you put 1 or 2 of them in the visible part and have one of them in the red. And they can just measure the temperature every minute or so. I found about 5 minutes works. If you read I have a link to their activity. If you read what they have them do it for 10, it's kind of up to you. So there's what it looks like. But the key thing here that makes it work is painting the thermometer bulbs black. Then they absorb the infrared, well, all the radiation a lot more, and it makes this a lot easier to measure. And then the thermometers, the spectrum isn't really very big. And so I have a link to these thermometers. They're this really cheap, small glass kind. And you can trim the scale around them. And here's 3 of them really close together. And so I have the ones I use here. So you can see I've trimmed the scales, because it's just plastic cut out, and then taped them together on the back. And so they're custom made for this. And you can see that I've painted the bulbs black. And then it's putting a white sheet in the bottom makes the colors look better. You don't have to do that. The key thing is, the sun is in different places in the sky. And so you'll have to tilt the box depending on the time of day. And so keep the lid as well. You can use the lid to prop the box up. Some people make a special little leg on the box so that's adjustable for different tilt angles. And so you can see here this one started, so the Earth will rotate while you're taking your measurements. It's another reason to go for 5 minutes instead of 10. But this one is, the Earth's rotated a little, so the infrared bulb's a little bit in the red here. And so when students were doing this, I'd walk around and look for that to make sure they kept it in the infrared. And this is typical data. These were some middle schools did this, and NASA published when they were testing out the activity. One time I did a workshop, and one of the teachers at one of these schools was in the workshop, and they're like, "That's my data." And then there's some resources there. Now, one thing that's kind of puzzling is Herschel, and usually students doing this find that the infrared has the largest temperature increase. Well, to discover infrared, all you had to do was show that there was a temperature increase. And I should make another point here. If you saw me doing the experiment, my box would have one more thing, a thermometer over in the shade part as a control, because the sun it's kind of like a little oven there. And so you want to compare the temperatures to another thermometer that's over in the shady part of the box. But it still works.
Dan, I have a question.
Yeah.
On your spacing of your thermometers, it looks like you have them really close. Wouldn't you want them a little further apart so that only one is in the affected area while the other two are used as control thermometers?
The idea is to measure the temperature in 2 colors plus infrared. I think you could make a strong case for having one in, say, the green and one in the infrared, and then a control off in the shade. So, and it makes it easier to arrange them, and you don't need as many thermometers. So I would agree that this is the procedure that NASA worked out. It does work, but if you saw mine, this one's sort of set that way, that there's 3 here, 2 are in the spectrum. The other thing is the dimensions of the box make it so the spectrum is a certain size. You can only get it so spread out. So you could experiment with a different box so that the spectrum would be cast further from the prism, and it'd be a little bigger then. So you could experiment around, but this works. So it doesn't mean it can't be improved on. Other people will ask about, well, what about using temperature sensors? And people have certainly done it, but you just end up with all these wires and stuff. I guess you can use wireless ones. You still have to paint them black, and this works. Just use it, and you don't have to measure the temperature that rapidly. And so why does this work? Because we know the sun peaks in energy here in the greenish yellow part. So why would infrared have the largest temperature change? It's not linear. And so it turns out the infrared is a little more concentrated. And so that's why Herschel measured the greatest temperature change. And usually you do when you do this experiment. So just wanted to throw that out there too. So this is a link to the activity with more pictures and details. This is a link to a cheap equilateral glass prism. And then Ward's has these cheap thermometers that I'm using, a 15 pack for $24.50. And so if you are just going to use a control and then two other ones, you've got, that's 5 lab setups there. This also could be done as a class where somebody could be saying out the temperature and the students have to write it down. You're only doing one. I think that would work. They like to be outside. And just a shout out to the website that they made for the Spitzer Space Telescope called Cool Cosmos. They've since reorganized it and sort of, I don't know, some of the things I liked no longer are there, but I checked it out in detail before I put this slide together for today. And there still was a lot of cool stuff on the Cool Cosmos website. And so there's a set of infrared picture galleries with different themes. I have one shown here, infrared cameras being used in by firefighters. And so this is the visual light image, and this is the infrared image. And so the firefighter, if he had an infrared camera, would see this person succumb to smoke inhalation probably. I always like the infrared zoo. Let's maybe take a quick look at that. And so they went to the, I'm pretty sure it's San Diego Zoo, and they took pictures in visible and then infrared. And some of the animals are more interesting than others. Well, there's a bunch of them. It's a giraffe. And so the patterns don't show the same and so on. So, and then they have a video. It's getting kind of dated now. It's called More Than Your Eyes Can See, but it's short and really covers the idea of the electromagnetic spectrum pretty well. Let's maybe watch a little bit of it. Oh, media not found. Oh, it's right here on YouTube. I did put a copy, a digital copy of it in the files too, if you'd rather have that.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all the colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom.
Jump ahead to the
How about elephants? What about a polar bear? about a rhinoceros? Check out the horns. A cat. Notice the infrared footprints. Deer in the dark. A helicopter. Notice the plume of heat from the engine. Earth movers with hot smokestacks. A car engine turning on and heating up. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem. But just like infrared light can penetrate some things that stop visible light, it also gets stopped by some things that let visible light through. For example, here's a piece of glass. And as you can see, none of the infrared gets through at all. If you haven't guessed, that's how the greenhouse effect works. Infrared light can't get through gases like water vapor in our atmosphere, which means that the heat is trapped and our planet is getting warmer. So what am I, an astronomer, doing with an infrared camera? Well, if everyday objects look different through an infrared camera, you can bet objects in space do too. For example, here's an image of the constellation Orion, which you're probably familiar with from the night sky. But now, let's look at it through an infrared camera. Look how much you're missing. Astronomers are also hoping to use infrared light to find planets around other stars. Planets don't give off any visible light of their own, making them nearly impossible to see close to a bright star. But in the infrared, planets give off their own light, making them much easier to find. Astronomers will soon be able to use very sensitive infrared cameras on a new space telescope, the Space Infrared Telescope Facility. And it should give us a whole new perspective on the universe. At that point, we'll finally be getting a more complete view of the universe. Right now, we don't even know what we're going to discover. There are so many wonders out there. We'll finally be able to see more than our eyes can see.
So there are affordable mid-infrared cameras now that work with phones and stuff, but this is a good way to bring in what an infrared camera would see into your classroom with a short video. They really show lots of applications of it. So it's one of my favorite science videos in less than 7 minutes there. But you can very easily make a infrared camera, but this is near infrared. And so near infrared is the wavelengths that are just beyond the red and then out to, there's a certain number, but maybe 3 times the wavelength of red light or so. And it turns out pretty much any electronic imaging equipment for consumers is sensitive to it. And so if you have something that shows a video image, it is sensitive to near infrared. However, the near infrared radiation degrades the image. And so inside these devices, they put a filter that blocks near infrared. So to make a near infrared camera, step 1 is you got to take this filter out. So you're not going to want to take apart an expensive digital camera to do this. But that's not a problem because there's lots of really cheap ones. You can get a webcam for less than 10 bucks. They come apart pretty easily, and you can remove this filter. Then you want to make it so only near infrared is getting to the sensor. And so now you need to replace the blocking filter with one that lets near infrared through, but not visible light. And there is a filter specifically for that purpose called a Ratten 87C. They're kind of expensive. You can find them, you know, on eBay and stuff for less than $100, but it's enough material you could make hundreds of these cameras, but you don't really want that. And so unless you get a piece and then, share it with people, that's an expensive solution. But it turns out exposed color negative works almost as well. Floppy disk material, not so much. And that's probably pretty hard to find now.
Floppy disk, what's that?
But you can bet that your grandma has exposed color negatives. And so back in the day when people had cameras that use film, you would take the film in or mail it in somewhere, and they would develop the film and make prints from the negatives. And there was always on the edge of the negatives, on the ends, would be parts of it that was, it's not exposed, it's unexposed. All right. But there's always, it's the part that comes out really dark when you develop it. And so you take a piece of that dark material and then that's your filter. And when you reassemble it, you have a near infrared camera. Now, even if you had all that stuff, some people aren't going to want to bother to do that, or maybe think they'll never get the camera put back together. Correct, I have a few cameras that I never got back together right. I've had some success though, but it turns out Sony made a camera that does this, except it has a little switch that just moves the IR blocking out of the way. And so you can just put the color negative material over the lens and it works. So this is some data that I collected with a spectroscope to show this. So this line here is the full spectrum coming from a white light source. I think I was using my overhead projector. This is one of the infrared blocking filters that are found in all these digital devices. And you can see it lets the visible through, but right when you start to get into the red, it drops down, and then it's not letting any of the infrared. The infrared here is going to be beyond 700 here. And so blocking it. So you take that guy out. These other three lines are the materials I was talking about. The blue is a Ratin 87C. It lets through all this infrared, but blocks pretty much all visible. This is the color negative. Hey, that works about as well. And if you find a old piece of negative, it's pretty much free. This is the floppy disk. The floppy disk material, all it's really good for is if you look through it yourself, you sort of get a sense of what the near infrared world looks like. But it's letting through a lot of visible. So what do one of these look like? Let's see. Here we go. There we go. So that is the near infrared camera that I have hooked up to the computer. And so there's our room in near infrared. It's not uncommon to have it come out to be almost all dark in a classroom. But Tom has the door open, letting sunlight in, and infrared is bouncing around. But now I'm pointing up to the overhead lights. You can see they glow on the ends where they're warm a little bit, but otherwise aren't very bright. Want to see what it looks like when you close the door, Tom?
Sure.
So Tom is going to block the sunlight. There's Val and Abigail. Let's see if we lose them here. Still sunlight coming in the back. There, pretty dark. So what we need is a infrared light to illuminate things, and remote controls are that. I'm shining a remote control into the camera now. And you can see it's picking it up really bright. It flashes on and off. That's why you get that. It's not staying on. But now I'm going to point it at my face. You get a little hint of it. There's still a little infrared in here, but now I'm illuminating my face with the remote control. There's some kind of cool things to show. I don't want to. I've been accused of spending way too much time on these infrared cameras in the past, and I don't want to do that because I have written a couple of blogs that show it all. Let me just show you one thing here. This is a $20 bill in near infrared. It's illuminated some. I have a still that I'll show you in a little bit, but notice that band of blank on it. That only shows in the near infrared. So there's a material on there that only shows up in the near infrared. It might have some counterfeiting aspect, but it also lets like vending machines be able to tell what denomination it is. So here are some pictures I've taken in near infrared. And so this was a student on Halloween in her giraffe costume. And then in near infrared, you don't see any of the pattern or anything. This is the $20 bill invisible, and then near infrared that we just looked at. This is a, what's being not found? Well, so this is a hot plate, obviously, and it looks like it's glowing red hot, right? But in the video, which I did put, well, not sure if I put it in there or not. I may not have it. But you can see my hand come in the frame, and I put my hand on it. No, I didn't put it in there. It's not that great. Then this is the swimming pool at Los Gatos High School, and you can see the lane markers on the bottom of the pool. And then in near infrared, you don't see anything. So the near infrared is not able to pass through the water, at least not to the bottom and then back out again. It's kind of cool. It looks dark. And then this is a piece of material invisible, and then in near infrared. And so I put this sign underneath it that's only visible in the near infrared. So the near infrared is able to pass through fabrics. And that's why the Sony camera, they ran into a little trouble when that first came out, because it has this feature called night shot. And on the front of the camera is an infrared LED, at least a set of them really, that sends out a beam of infrared. And if you put it in night shot mode and you go out at night, you can see stuff. So it's kind of cool. It's like having your own night vision camera. But people noticed in the daytime, when they had it in night shot mode, there's all this infrared light out from the sun that some fabrics you could see through. And that made some people uncomfortable. And so Sony modified their camera so that it wouldn't work in sunlight. And so they still sell them, and you can find them on eBay pretty cheap. I happen to just have one. And so instead of spending the next 3 hours talking about this, I wrote everything I know about these near-infrared cameras and near-infrared radiation and stuff in 2 blog posts, which are there. And there's, if you think these pictures are cool, there's a lot more there, and some how to make your own camera stuff, etc. So you have some diffraction stuff, Tom?
Yeah.
I'll go through these slides, and then we can like show some things. Okay.
Sure. Before we get diffraction, you want to talk about UV beads and
oh yeah,
the other end of visible light. By the way, one thing I really miss is the old days of flip phones, because that was one of the tricks I like to do when we were teaching, non-visible light was I'd ask students, how many of you have brought your infrared detectors with you today? And silence. And I was like, how many of you have your flip phones with you today? All the hands would go up. And I said, and I would grab my nearest remote control and say, here, take a picture of me putting the remote control, and it would totally light up. And they'd be able to see it. And
So I didn't even try it with this, but try this camera pointed at it. Let me get real close.
I don't think it works for iPhone cameras.
It'll work on the selfie one sometimes. So that means, so they've made way better infrared blocking filters now. And the better optics tend to have those.
Curse progress.
The selfie camera, I don't think this lets you turn that on.
Well, the other thing I like to do on the other end, what do we go here? Is ultraviolet light. So I said, how many of you have your ultraviolet detecting equipment handy with you today? How many of you have a driver's license? How many of you have $5 bill or more? Okay, yeah, so I said, get those out. Just if you want to volunteer. And I get out the little UV light and just pass it over. And you'll be astonished how many kids, and I'm sure this is even worse now, because they haven't had cause to travel during the quarantine, but how many kids didn't realize that when you shine ultraviolet light or black light over driver's license, there's a UV watermark, and they would see, the California flag or another picture of their image, and that would just shock them. Or you would see a little stripe in a $5 or $10 bill that's not there in visible light that they have for fighting counterfeiting. Another thing is these UV beads. A little necklace I made with it. I made a little necklace out of these UV beads, and these they look kind of white, off-white in normal, and unfortunately the batteries seem to have died in my UV light here, but when you shine UV light on it, they slowly start to change colors. But if you really want them to change color quickly, I'll get it right back.
Oh, it's going on.
And I promise I didn't do a switcheroo. If I was a magician, I would try to be a much more slick one than that.
You look a little tanner too.
So again, these are made of a chemical that will absorb ultraviolet light and then uses that to trigger these different colors. You don't know which color you're going to get until it's exposed to the UV light. And the fact that the sun is a much greater source of UV light than a UV light is, I think tells you something about how much UV light you get from the sun.
Oh, this one's working.
Oh, that was, oh, maybe that was, let's see. So here are
I have some more.
Here are some untriggered UV lights. So if I put these under I don't know if the material the baggie is made of might be blocking.
That's the whole experiment, right?
Well, let's see. Let's do a controlled experiment. I'll leave some of them in and some of them out. So yeah, the ones outside the baggie are changing color more quickly.
But they do change in. It's not as, yeah.
It's kind of like you can't get you can get a sunburn if you have a window between you and the sun, but it just takes longer. I have students every once in a while will have a t-shirt where the t-shirt was made out of this material. It'll be a black and white picture, but when they go outside, it becomes color. And I've asked students, you care if I show how this works? And the shirt with the black light, it takes forever for these shirts. And then I think, step outside and come back, they'll turn around.
makes you want to wear sunblock.
Yes, absolutely.
Now, what are these beads called, Tom?
UV beads.
Why are they called that?
Because they were discovered by the physicist Ulysses Vanguard.
Because they turn color in UV, right? However, this is a violet laser. It shines at 405 nanometers, which is in the visible.
Camera actually is not working.
It's not working. It's not showing it.
No, I'm terrible at this. I know
Let's
Paula.
look. Aha! They're changing. Not all of them, but in my experiments, I found 3 out of the 5 different colors change in the violet laser.
They're much more dark than Tom's look.
Well, I think in the sunlight they'll turn pretty dark. So
Let me grab a handful and take
that
them
is
outside and
just
see what that looks.
disappointing. Grab a slide. There we go.
Here they
Stand
are
back.
after a couple seconds in the sunlight.
They turn it dark.
There we go.
No, you're doing great. I'm watching it.
I'm making people at home sick.
Okay, I've got it on the slide now, so we can take a little break. So these are just some activities you could do with UV beads, even though we know they're not really UV beads, only 2 of the 5 different kinds. What light sources make them change color? You can use the beads to discover what materials block UV and short wavelength light, like the plastic bag apparently blocks some of it. And Tom just took them outside, put them in direct sunlight, but what if you kept them covered and went into the shade? Is UV bouncing into the shade, or are you out? How about on a cloudy day? Is UV getting through the clouds? And this is probably the typical thing people do with it, is test different sunscreens. And I recommend, this is what the Exploratorium says to do, put a plastic sheet over them and apply the sunscreen to that, like handy wrap or something. Then you don't get the sunscreen on the beads. You'll have to wash it off to do the experiment again, but you can see what kinds of sunscreens work the best, or sunglasses. And then again, I've found the UV bead fraud. This was my tweet about it, clearly showing visible light gets 3 of the 5 to change noticeably. Maybe that 4th one changed a little, not much. So I was shocked when I did that.
Dan, just a question on the sunblock. You said you could put the sunblock on plastic, but isn't the plastic, doesn't that block UV? So that would kind of cloud your experiment?
You would want to find one that isn't blocking much. And that's why the handy wrap or something like that is very thin. So it would not prevent you from doing that experiment.
Or just use one without any sunscreen on as a control.
Yeah, you'd have a control as well. But this bag that we were using just a little bit ago that looked like it blocked it, it wasn't. It just slowed it down a little bit. So it did work a little bit like it filtered some of the UV out. But yeah, I would say if you're really pure scientist, you would have to apply it directly to the bead. But then you're going to have to clean them, but that's not, I guess, a big deal. Science teachers are always putting weird things in the dishwasher, right? So Arbor Scientific has a pretty good handout that goes with these that explains the chemistry of the color change. I'm not going to go into that because this isn't PTSOS, but it's interesting to read. And these are one of the raffle items. Is how many? 5 beads?
5 times 20 beads, 100 beads.
100. Whoa. So that's one of the raffle things. Then just since we have the violet laser out here, so is the violet laser showing up in the, oh,
You need to change the camera.
so let's see, is the violet laser, oh, it shows
Yes.
up on the screen pretty well. Looks weird on the whiteboard, it's purplier. Oh, what is going on there?
Oh, white one, green one.
And so that is phosphorescent material. I put some glow-in-the-dark paint.
If you scan up about 1 meter above that, you'll find my glow-in-the-dark Enterprise D.
Very cool.
That's pretty good. That works better. Oh, you can almost see the whole thing there. So science, again, the violet lasers are part of the raffle prizes.
Might want to mention some of the violet lasers have the little filter on them that you can take off, but it lays out the beam.
Yeah, one year when we got these, there was a little thread-on piece on the end. And when you turn this on, it made this like whole little laser light show, but it just screws off and you can use it in regular mode. Let's see. So another property of waves is that they diffract. One way of thinking about diffraction is it's them spreading out when they go through a narrow opening. And if you have waves in the same place at the same time, they interact or interfere with each other. And if they interfere to produce a wave with a bigger amplitude, we call that constructive interference, although it might produce something that destroys something, but it still is constructive interference. And if they produce a wave with a lower amplitude, it's destructive interference. We did some of that with sound in the last workshop. And what's cool is with light, that means you get places that are dimmer and places that are brighter. And that was famously done in Thomas Young's double slit diffraction experiment. And he was able to do his experiment and explain it in a very elegant way so other people could repeat it. That this is when people really started saying, hey, light is a wave. Because Newton thought it was a particle, and Newton had a lot of sway in the physics world. And so his ideas held, even though there were lots of observations suggesting that light was a wave. And Thomas Young's experiment pretty much convinced even the most entrenched holdouts. And my understanding is the key step here is this initial slit letting sunlight in made the light more coherent. With us, we don't need to do that step because we have lasers now. And that's one property of laser light is it's coherent. And so when the coherent light hits the two slits, you get it spreading out like that, and it's spreading out like that, and then you get this very geometric interference pattern. And wherever two crests are lined up, you get a bright spot, and wherever you get troughs, you get a dark spot, and or a crest and a trough. And so you get this set of fringes that show up, and Thomas Young was able to explain those very carefully and convince people that light was a wave. So it's sort of an important historical experiment that you can do in your classroom. The geometry of it is shown here. We have these two little dots represent the slits, and this would be perpendicular to the slits. And then off here is a spot where we're getting constructive interference. The intensity here, you can see a peak. And so we're getting the wave that came through here, and through here is one wavelength difference in path length. And so if it's coherent light, that means they both their crests are lined up, and so we get the constructive interference. That's where the first bright spot would be. And so we have these similar triangles. And if you assume this angle is small, which it is for double slit diffraction, you can set the ratio of the wavelength to the distance between the two slits equal to this distance and this distance. And so these things students can measure. They can measure how far that out is. They can measure this. They can be told the slit spacing or the wavelength and solve for the other one. And so it's pretty simple math to do it. And if they can handle sines and tangents, you can have them do it that way and find out that it's pretty close to this, that the small angle approximation for double slit works pretty well. Multiple slit, a little harder to understand, but it works the same way mathematically as double slit. And so if you don't want to go into this, which they can still see some of the geometry going on there, you don't really have to, because the end result is the same, except maybe the small angle approximation doesn't work as well. I was doing something a little bit a couple weeks ago at work, and I was like, you know, it's almost maybe not a small angle approximation. So I did it both ways, and I got almost the same answer. But it was kind of interesting to do it both ways. So if you have students that are capable, they can assess whether it was a good thing to do to use the double slit or the small angle approximation.
Dan, you mentioned that lasers are coherent, right? And they meaning they all have the same have one wavelength. Are they also polarized, or does the angles go off at?
I don't think they are. Well, we could find out, right? No, they go. I think they go through polarized material. But once they go through, they'd be polarized, right?
Right. Okay, thank you.
And maybe, you know, another way to get polarized light is to shine it at a large angle of incidence off a smooth material. And that might polarize it as well. That's why we wear polarized sunglasses, because when light glares off the ground, a lot of that glare is polarized light vibrating horizontally. And so polarized sunglasses are polarized vertically.
Is that why you can see fish better in the water when it's when you have polarized sunglasses?
That makes sense.
Yeah, it gets some of the glare off the top. Yeah, if glare from the reflections off the top of the water, I would assume so.
So the glare overwhelms the light coming out of the water. So
it could just be the fact that you have any sunglasses on. I don't know.
No, it needs to be polarizing, because it's reducing the glare, because when light reflects, it becomes polarized parallel.
Depends on how you're looking at those fish. If they're straight down, then it wouldn't matter, right?
Well, usually you're in a boat.
They're not straight down. They're not straight down.
Okay. Let's see here. So I threw that in. We got to that. So this is so now that you can get inexpensive lasers of different colors. This was sort of a activity for students using diffraction, You wouldn't have to do it this way. I just thought it was cool to set all three up together. But you could certainly have one off in one part of your room and another in another part and so on. And really you just have these four variables, and given any three, the student should be able to solve for the fourth. But what's kind of cool is they can solve for the wavelength of light, which is a really small quantity, by doing these other measurements and given what D is, which usually is printed on gratings. They let you know what D is. So this would be just one approach. Given the wavelength, say, of the top one, say the red one, they can measure X, which would be this, and L, which would be the distance from here to the screen. Ideally, what I recommend for X is they measure it here, and there's another red spot over here somewhere, and then divide by 2. Then you get a little more accurate answer. And then they could solve for the spacing in the grating, little d. And since I have these all set up in the same place, in this case, little d and L will be the same for all three lasers. That's maybe an argument for not doing it this way, because you could have different L's for the other lasers. And now that I know little d, I can measure X and L and solve for the wavelength of, say, the green one. And then for the violet one, I could predict what X would be and then measure it, just to get several calculations in, some practice. And then you could also, if you wanted, have them evaluate the small angle approximation. You can see red is diffracting the most. And so that might be the one to evaluate and see if your value for D is significantly different if you use these two equations versus this one. And then this is what it looked like now. You might have your laser. I don't know, I think the Enterprise thing was just as good, Tom, if not better. But that was just one laser. We'll definitely do that sometime in the future. So you had some stuff with diffraction.
Yeah, just a couple of ideas for other in-class activities that I do. The way I like to frame it is, instead of solving for wavelength, what I like to do is, let's measure the thickness of something that ordinarily would be very, very difficult to directly measure the thickness of. The first thing we do, I just left it, was the CD. So CD is like a diffraction grating plus a mirror. So you have tiny little grooves, microscopic little grooves or pits in the CD. And then, but it's reflective behind it. So if I shine a laser, by the way, I could have 1,000 free hours of AOL. If I shine it, I get central bright spot, first order bright spots, and the geometry is just the same as if I had diffraction grating, except instead of the light just diffracting, it diffracts and reflects, but I can still set it up. And if I know the wavelength of my laser, I know the distance between the first order bright spot to the central bright spot, and the distance from the CD to whatever I'm projecting on. I can calculate the pit spacing or the thickness of each little groove on the CD, and then knowing how wide the CD is, you can calculate how many grooves are on your CD. The other thing I like to do is have students measure the thickness of their own hair. The way I tend to do that is I have students either pluck, scissors. Sometimes they can just find a hair that's already on, a comb or a hairbrush they have handy, and I have them tape it to a little microscope slide. You could also have them cut out a little hole on an index card and tape it. And I set it up. You need a pretty, when you have the CD, the spots are spaced out pretty far apart. And that's because the thickness of the grooves on the CD is microscopic. hair is thin, but it's not microscopic. So the spots are going to be a lot closer together. So I usually have it set up on one side of my room. Students have a microscope slide with their hair on it, and then and it's being held up by a little piece of modeling clay. And then they have a laser, and then they project onto the far side of the room, and they have their interference pattern. And I have them project. I used to have them just project onto a piece of paper. Now I have a class set of these little portable whiteboards. These are just kind of handy things to have. So they project on a little portable whiteboard, and they can draw where the central bright spot is, where the first order bright spot is, and then measure the thickness of their hair.
I put a handout, just kind of notes written up for teachers wanting to do this called diffraction activities. And that's in the my folder, even though Tom and I both do these. The hair one is single slit diffraction. So they measure to the first dark spot. Well, they would know either way. You don't have to tell them that. Because the hair is
technically it's a single slit pattern. I fudge it a little bit, and I still frame it as double slit, as saying, well, the light that diffracts around one side of the hair interferes with light on the other side of the hair.
It's not like they're going to check it and say, no, wait, my hair is.
Technically, they're all off by
500
because of it, but that's a level that I don't get into, at least in regular physics. In IB, we do cover single slit diffraction a little bit. So those are my in-person diffraction labs. This year, like so many other things, I've been using PhET. So this was the bending light for PhET. Find the diffraction version. And it's loading.
The fiber sort of works. There's too much.
It's the one called wave interference. And you can set it up to, turn it on. Right now it's set up to emulate what are supposed to be water waves. So that's what this little faucet looking icon is. This is meant to emulate sound waves. So that's what the little speaker icon is. And then this thing that looks like a bullet or lipstick, or actually what it looks like is one of those big old bullets from like the old Super Mario Brothers game. Well, I think it's supposed to be a laser pointer because this little thing represents light, and you can have one slit or two slits, and you can include a screen so you can see where the central bright spot is. You can see the first order bright spots. And I wrote a lab activity that goes along with this, where it basically walks students through and they recreate Thomas Young's experiment. And by the end of the activity, they can calculate the wavelength of light based on all the measurable aspects that Young was able to measure. So this is how I've been doing diffraction at distance. Pretty much what I got on diffraction. And all my write-ups, both in person and distance learning, are on my website.
So I'm always looking for something new, or at least new to me. And these laser distance meters. They've been out a long time, but they've come way down in price. And, you know, they measure distances, which could be useful for physics. So if I want to know how far Tom's back wall is from here, I just hit it and I see a little red laser spot, and it immediately tells me it's 10.39 meters away. So I can see all kinds of things I might do with just measuring distances. The kids don't have to get tape measures out and things like that. But somebody thought of this idea, which I thought was pretty cool, and that's why I got one. It wasn't to measure distance. So I have this empty cup here, and let's see how tall it is. So I just hold this. There's a emitter and then a collector. And I want to make sure I'm not blocking either one when I do this. I just put it there. I'll do a couple just to make sure I'm doing it right. So it says it's 0.109 meters, or about 11 centimeters. And it doesn't work really great that close, but it's about 11 centimeters. So that worked pretty well. And so how does this work? I'll tell you a little bit more detail about that. In general, though, you can just figure out how much time it took the laser to bounce off whatever you pointed it at. And then it assumes the speed of light in air, and it knows it's a round trip time, so it divides the time by 2, or it calculates the distance and divides it by 2. So it's really a pretty simple calculation. However, we can fool it. Now I filled that with water. So is it going to tell me it's 11 centimeters now? Now it thinks it's 0.148, or about 15 centimeters. Well, that makes sense because it's assuming that it's speed of light in air. We know, at least one model says, that light slows down when it goes through water. And so it took more time because it was going slower. The laser distance meter doesn't know that, so it calculates the wrong distance. So it turns out you can figure out the speed of light through water with just those 2 measurements. It's really the ratio. So 0.148 over 0.109. I'll let you guys do the calculation. I have a slide. I did my own. Oh, yeah, you're. So it calculates the distance as I just explained. So here I'm doing it on the side. But X is the distance, so that was 11 centimeters in that case. And then the wrong distance was about 15 centimeters. And T is the time in air, T prime is the time that it actually took. But the laser distance meter didn't tell me that time. It just gave me a distance. So I have to know how it got that distance. It assumed speed of light in air and measured the time. So I also have the speed of light in air, speed of light in the medium. So distance is speed times time. Going through water, oops, the distance again is speed times time, but it's this longer time. And the laser distance meter again didn't tell me that, but I can figure it out. It'd just be the distance it told me over the speed of light in air, because remember, that's all what it's always using. So the speed of light through water is just the distance, the actual distance over this time that was measured going through water. And I know that the time was X prime over C, so I get this. So the end result is simple, and it's really not too tough here. And so the actual distance over the wrong distance times the speed of light would be how fast it's going in water. And we know that ratio is also the index of refraction. Oh, do you have a calculator up here, Tom? Or
Should be one up there somewhere.
oh, I know. I'm just curious. Okay, so 0.109 divided by 0.148. And I wanted to go the other way, didn't I? For the index of refraction. Because that's what is it, water 1.33 or something?
About 1.33 if I remember right.
And I get 1.36. And so it's not too bad. There's an issue with where I'm exactly holding it. I couldn't actually get it right down into the water, which would have made it come out a little better. And so this just goes over an example. I'm using a different glass, so we don't need to spend a lot of time on that. But I got 1.37 for that. So I did better live. So that's pretty good. So I just thought that was a great use for this. And I can think of a lot of other ones, especially if I taught math. So if you wanted these, and you knew a math teacher that liked to have their kids doing activities and things, I could see a lot of great activities for this. This is the one I have. It's 20 bucks. I got it for 18. The last time I checked, they raised the price up to 20. And it does some really amazing things with the distances. It can measure heights of things. So you just point the laser at the top and then point it straight out. So there are other ways of doing that. And then if you're interested in how they work, these are some of the resources I found useful. But this is my explanation of how this particular one works. There are other laser distance meters that are used for all kinds of different purposes. And so what this one does is it modulates the brightness of the laser in a repeatable way. It's a sinusoid. And so this modulation, this alternation in the intensity, has a frequency and a wavelength. It's not red, it's not the laser light, it's the intensity function. And it measures the intensity of the laser light coming back and compares it to what it sent out. And so it can see if there was a phase shift. And so this angle is the phase shift. And so whatever fraction of 2 pi that is the fraction of the wavelength of this modulated wavelength it is. So if it's a half wavelength, then this would be, well, it comes up to a half wavelength. This would be a pi here. So you get 1/2. And so this is how they solve for the distance. They figure out the change in this modulated wavelength. It's that phase shift times the speed of light over 2 pi times the frequency of modulation. And then the distance is half that because it has to go out and back. And so the maximum distance that you can measure is a half wavelength. So mine, this one I have, could measure out to 40 meters. And so its frequency of modulation has to be at least 3.75 megahertz, which is, I tried to measure it. It's too fast for any of the equipment I have at work. But that's a short explanation of how they work. And I think we should do some electricity stuff. What do you think, Tom?
Sure.
So this is sort of connecting electricity and light here. I'm just going to leave this slide on here. We're not going to get to everything, so I'm going to skip around a little. That's one good thing. If you see something you're interested in, there's some place to start here.
There is an Arbor Scientific does make a device for measuring Planck's constant, and I do have a write-up for lab activity that goes with that. That's on my website.
So this one is just experimenting with Planck's equation and the fact that higher frequency light is more energetic. And this was something I did and had fun with, but I don't see it as being applicable here, but if you're interested in what happens if you stick an LED in liquid nitrogen, there's a lot of stuff there. This is a green one. And it turned yellow.
Cool. Green to yellow.
And it turns out it really shouldn't do that, but it did. And so if you're interested, there's enough to keep you busy all day tomorrow. And how an LED works. So let's do some electricity stuff. And so this is kind of a simple activity. It's a sort of a circuit tester or continuity tester. And this one, unfortunately, is no longer available, but we do have a substitute we'll show you. Tom has. And I think some people like this one more. It's not as cute, but
Does make me want to go home and put in my DVD of Forbidden Planet.
what if I touch the other end? It doesn't work. Well, we can't. It's COVID. Oh, it didn't work.
How about? Nope.
Oh, that usually works.
Huh.
The chicks are better. I'm sorry. We've done that before. Try one more time.
Okay, let's try.
Huh. Well, I know we got that working before. But with the chick one, you can even get, a whole chain of people. Well, I'm bummed, but you can try one if you get that as a raffle prize. Here we are trying to fix that out. Zoom in on yours. And so it's not as simple as you might think. The way this works has something to do with the measuring capacitance, sort of. It's not just running electricity through you, but it does go through your, it passes through your skin and tells the circuit that it's doing that. You can look it up, but most people just say it's completing a circuit. And you want to do, you got the Van de Graaff stuff there. Want to do that?
Sure.
Well,
Get his stuff off the table.
Tom is getting ready. I'll point, this is, I did put this video in my files, but it's a scene from National Lampoon's Christmas Vacation where Chevy Chase lights up the house for the first time. It's sort of a running gag in the whole movie. He's got all these lights on the house and they won't turn on. Finally gets them to turn on, has something to do with a switch he didn't know about. And they show the whole town dimming. And then for an instant, or 1.7 seconds, according to my calculations, they show his electric meter. And so you can, from the video, figure out how much electricity it cost him to run his lights for 1.7 seconds. And I wanted to know, well, how much is it going to cost him? Let's say he leaves his lights on for 12 hours all night long. Well, $1,339,747. So he was probably lucky he couldn't get them working for a while. So that clip is in there if you're interested. Go back to.
Hopefully this works. I haven't tested it yet today. So these are a little expensive. They're about, what, $750 for a new one, but they are a lot of fun. Kids really get a charge out of them.
There's a hand crank one that actually works pretty well, and then they don't think that the electricity is coming from the wall outlet. That's less, but it's better to have this one.
Now, the first thing I did was I put a wooden board down here just because I wanted to appear a little taller. And also just get a little more insulation between me and the ground, because that's often where the discharge happens. So turn this on. And
Your hair's deep.
So this is not the, I don't have the most powerful one in the world, and it is a little old.
Sounds like it's working pretty well.
But, so, okay, so it is working. So just go for it.
If you don't stand on something, though, you might get a good shot.
Well, since my hair doesn't quite work for this demo, I have this little cat toy, which is basically little strands of metal foil, and you can see what's going on here is they're all being charged by the spandograph, and since they're all being charged the same charge as each other, which in this case is a negative charge, they're repelling each other. Another thing I like to do, off for a second, zap at discharge. I like to show off my Mad Jedi skills. Put on some pie tins. Also gives me an excuse to have eaten, what, about 8 pies before I did this, and then so they become like charged and repel each other. What I do is get cat toys are so useful for physics. So here's another one. So this is a little lightweight ball. It was feels like it's plastic, but coated with some sort of metallic paint or something. So if I bring it nearby initially, notice it's kind of being pulled toward it. So it's being attracted. But then there was a zap, and then all of a sudden it was repelled. And so what was going on there? Well, initially, if this becomes negatively charged, and this is neutrally charged, but a conductor, then the negative charges that are in this will repel to the far side, and that leaves the near side with a net positive charge. The near side is closer, ouch. The near side is closer, so the attraction trumps the repulsion, and it was attracted to it. The same charge polarization that explains why rub a balloon on your head, it'll stick to the wall. But when I got close enough, here's a little zap, and there was some discharge, some electrons jumped over, and now both, oops, so now when both are negatively charged, then there's going to be a repulsion. And I can discharge this by touching it and start the process over. And if I do it this right, I can get it to kind of orbit. Now you might have heard the little zap, but not seen the zap because the little lightning bolts are so small. And one way to fix that is because as soon as something gets zapped, as soon as the first tiniest little zap hits this sphere becomes negatively charged. This sphere is negatively charged. Now the two spheres are repelling each other, so there's nothing inspiring the charge to want to jump off of one negative sphere to go to the other negative sphere. But if I grounded the second sphere and it doesn't build up a negative charge, well, that's not good. So
soap bubbles do something similar to the cat toy. If you blow a cloud of soap bubbles, they're polar, right? They get attracted, but the first one that hits kind of sends a little spray, and some of that's negatively charged, lands on the other bubbles. They stop and then turn back around, go the other way. So you get soap on your hand graph.
Let's see, where did my masking tape go? I'm just going to tape this alligator clip here and then connect it, oops, and connect it to ground here. So now, every time there is a little bolt of lightning, a little zap from the Van de Graaff to the initially neutral sphere, that excess charge is then dissipated to the ground, so it doesn't build up a negative charge. Go ahead and turn the lights off. So this is, or at least it can be, a little bit more impressive. This is pretty impressive. It definitely makes me feel like I'm getting my mad scientist on. If I stand behind it with my black shirt, you can see it even better. And if I separate it, the bolts are even, takes longer from one to one, they're pretty powerful. It's alive! Okay, I can't top it.
But see if Abigail stands on the wood.
Sure, you want to try standing on the wood? And
that was worried you're going to shock yourself.
And then just put your hand on it to start.
Here we go.
You just put your hand on it to start, and then I'll crank it up. And then this. I've never had a lot of luck getting air to stand with
It's
this.
gonna be really dry and.
Yeah, I've gotten arm hair to stand up. Either that or my spider senses were just making
It started.
Okay.
Yeah, on the sides. Shake your.
Oh, I'm starting to see it on your bangs.
Yeah, keep doing that.
By the way, if you're ever anywhere, like out in the world, especially if you're on a mountain or somewhere, and you feel yourself start to do this where you're at, don't be there anymore. You're at a place that doesn't really be constructed.
Okay, take your hand off really quick. There you go.
Want to try it with your hair, Dan?
Yeah, that's how I lost it. It just shot up to the ceiling. Yeah, this is a lot like the one we had. Hope your computer's okay. When I used this in Science on Saturday, it affected their camera.
Huh.
They started doing all this weird stuff. Let's see where we're at here.
It used to mess up my smartboard back when I had a smartboard. Well, the company that made it stopped supporting, software updates, so the smartboards became Doppler.
So there's, other stuff in the slides here that we're going to run out of time, but it's just, you can use it as a resource. So if you're doing circuits, Hewitt has kind of a clever way of showing it using a car battery. And so there's some URLs there showing that. You can see the setup there. Another raffle item. Here are some good magnets, but maybe you've seen these before. They're called magnabuzzes. There's 2 of them. And what you do is you hold them in your hand and you use your thumb to separate them about 1 centimeter and throw them up.
We can't see them. Can you show them? We have the slides in front.
You could hear it though, right? The buzz part.
Absolutely.
So is that working? That was a magna thump. Kids love these. They do wear out after a while. They get a little rough, but when they're new, they're really cool. But there's some good magnets, so I just put some activities you could do with magnets on the slide there. And they're hematite, which is also interesting. The same root for hemoglobin. Hematite was found on Mars. It's one of the reasons Mars sort of has a red color. And so that sort of means there was water on Mars, so a lot of cool stuff with that. And there's some distance learning circuit stuff here. Definitely, I would check out this virtual escape room and crack the circuit, these first 2. And then this is just something I've been working on at work. So we're not going to get to that. And you can see I got way too into it.
Crack the circuit is really fun. Students really like that. I had my IB students do that the other day on our first day of electricity. It's just a fun little introduction to the topic.
You want to show, since you got your motor working, you want to show that, and then I'll wrap it up here.
So I got this activity from the Exploratorium. They call it a snack. And it's just a way to build a little stripped down motor and have a coil magnet. And I had it kind of working earlier. Let's see. It's a really cool activity to do when you're covering either circuits or magnetism. Oh, there it goes. Well, you saw it. Oh, crap, you didn't see it. Well, okay, let's try one more time.
That didn't happen, did it?
Oh, there it goes. You're seeing it.
Let's go for 30 seconds or you don't get your points.
But one thing I liked about this activity is I grade the students 0 or 10 points. Did you get it to work? Great, there's your 10 points. You don't have anything to write, I don't have anything to grade. Everybody leaves the day happy.
You're close. I think you have to have more balance. So students who got this far would definitely get it working.
Often if you squeeze the sides of the cup so that the clips kind of separate a little more, that is enough to kind of get it going. Many of my students find.
And technically you just have a short circuit battery for this. So the batteries kind of, they get a lot of use with this lab, have a lot of extra ones. So I think we covered all the raffle items. And I forgot to mention that this is a raffle item, the Pi 10. 6 of them. Oh, not the Van de Graaff. So think of what raffle items you want, and they are all going to show up to you in a USPS flat rate box in a week or so. So everybody that's in attendance right now will get everything we mentioned as a raffle item. And we had some issues with the lasers. I think they're working, but last year we had them all ready to go. We even put batteries in them. Then they've sat for a year. So if your laser's not working, well, you've just got a cell phone microscope lens. And so we're going to send them out anyway. So if they're not, if one of them isn't working, use it for that, or try a fresh battery. They might work, or maybe there might be some corrosion in them or something, but they were working a year ago. So hopefully we'll see people live next year and have a good end to your school year. You've made it this far. Don't give up. Hang in there. We're almost there. And hopefully we did some things that will help you and your students here on out. Bye.
May you all live long and prosper.
There you go. So we'll see you soon.
Thank you so much. This was wonderful. And I definitely miss seeing y'all.
Yep. Thanks for spending your Saturday with us.
Thank you very much.
Right here. So
Thank
we're
you
going to
so
start
much.
packing up the goodies here. So enjoy those.
Thank you.
Thank you all. Really
Thank
appreciate
you.
it. Great
Thanks.
day.
Have a great day.
You too.
Stay healthy.
Thank you.
Beautiful day here.
All right,
Bye,
bye. Thank you.
Hello.
Dan, are there any
Hey, Larry.
What?
are there any summer opportunities at the lab? You know, you used to share like summer programs or workshops or whatnot that might be going on for teachers.
At Livermore Lab, they're probably doing it online again.
We're doing the Teacher Research Academies, and it's all online again.
So go to search LLNL Education and look for Teacher Research Academy. I am not involved with that anymore, but I heard more about it after last year than I've ever heard all the time I've been there, because they were reaching people all around the country. I did some workshops for teachers in Virginia, and they were telling me about it.
Fusion Astrophysics runs the week of June 14th to June 18th. I can tell you that.
Very cool. Thanks again. See you guys next time.
Take care.